4 billion miles from the Sun, in a region of space so distant that noon looks like midnight, a machine the size of a grand piano is dying. Its heartbeat grows weaker with each passing year. The plutonium dioxide that has powered it, since before the iPhone existed, now decaying towards silence. Every 12 months, another 4 watts slip away into the void, and the engineers at Johns Hopkins Applied Physics Laboratory must decide which instrument to sacrifice next, which eye to close, which ear to shut down permanently so that something else might continue listening. By 2040, perhaps earlier, New Horizons will fall completely silent, its radio transmitter finally unable to muster the energy to whisper across the gulf that separates it from Earth. When that moment comes, no one will know. There will be no death rattle, no final transmission, no dramatic failure. One day, the Deep Space Network will simply stop receiving its signals. The spacecraft will continue on its trajectory, utterly alone, for billions of years after, a frozen artifact of a species that once dared to throw a piece of itself toward the stars. And yet, right now, in this precise moment as you listen to these words, New Horizons is still alive, still measuring, still transmitting data that takes over 6 hours to reach Earth, even travelling at the speed of light, still discovering things about a region of space that no spacecraft has ever visited, in numbers that no astronomer could have anticipated when the probe launched in 2006, with the modest mission of photographing a single dwarf planet for a few frantic hours. The spacecraft that succeeded too well. That is how the mission scientists describe it among themselves, equal parts pride and wonder in the phrase. A probe designed to do one thing and one thing only, a flyby of Pluto that would last less than a day after nearly a decade of travel, that somehow refused to stop being useful, that kept finding things, that transformed a planned retirement into an extended expedition through the most mysterious region of our solar system, a place where the leftover rubble from planetary formation has been preserved in deep freeze for 4.5 billion years, waiting for someone to come and read the record. This is the story of what happened after Pluto, after the photographs that made front pages across the world in July 2015, after the heart-shaped nitrogen glacier and the mountains of water ice, after humanity collectively gasped at the first clear images of a world we had known only as a blurry smudge since its discovery in 1930. This is the story of a spacecraft that should have been finished, that could have been switched off with full honours and a triumphant press conference, but that instead was pointed toward the unknown and told to keep looking. What New Horizons found there, and what it continues to find as its power dwindles towards zero, may reshape our understanding of how the solar system formed, and it discovered all of this by accident, in a region of space that exists precisely because of its insignificance, a belt of frozen debris that the ancient processes of planetary formation left behind like sawdust on a workshop floor. To understand why New Horizons kept going, you must first understand where it went after Pluto. You must understand the Kuiper Belt. The Kuiper Belt begins roughly where Neptune's orbit ends, about 30 times the distance from the Sun to Earth, and it extends outward for perhaps another 20 astronomical units beyond that. If you imagine the solar system as a city, with the Sun as downtown and Earth as a house in the near suburbs, then the Kuiper Belt is the rural farmland at the very edge of the metropolitan boundary, the place where streetlights end and the darkness of true countryside begins. It is not a belt in the sense of a solid ring, but rather a vast donut-shaped region of space populated by millions, perhaps billions, of frozen objects ranging in size from grains of dust to worlds nearly the size of Earth. Pluto is a Kuiper Belt object. So is Eris, discovered in 2005, which triggered the controversial reclassification that demoted Pluto from full planetary status. So are Makemake and Haumea, and thousands of smaller bodies with names like Quaoar and Sedna and Orcus. But for every named object in the Kuiper Belt, there are 100,000 anonymous ones, chunks of ice and rock tumbling through the darkness, unobserved, uncatalogued, waiting. The Kuiper Belt matters because it is a time capsule. When the solar system formed 4.5 billion years ago from a collapsing cloud of gas and dust, the inner regions grew hot enough that volatile materials like water ice and methane and ammonia evaporated away, leaving behind the rocky cores that became Mercury, Venus, Earth and Mars. But in the outer reaches, beyond the snowline where temperatures dropped low enough for ices to remain solid, these volatiles survived. They clump together with rock and organic compounds into what astronomers call planetesimals, the building blocks from which larger bodies would eventually form. In the inner solar system, these planetesimals smash together and accreted into planets. But in the Kuiper Belt, the distances were too vast and the densities too low for this process to complete. The material out there never finished coalescing. It remains today, much as it was at the beginning, a museum of primordial ingredients scattered across billions of cubic miles of nearly empty space. This is what makes the Kuiper Belt scientifically precious beyond measure. Every other region of the solar system has been transformed by heat, by gravity, by collisions, by the passage of eons. The inner planets have been resurfaced by volcanism and weathered by atmospheres. The gas giants have consumed and processed their original materials beyond recognition. Even the asteroid belt between Mars and Jupiter has been stirred and modified by Jupiter's immense gravitational influence over billions of years. But the Kuiper Belt has been preserved in cold storage, largely undisturbed since before Earth existed. The objects there are fossils of the solar system's birth. New Horizons was never supposed to study the Kuiper Belt in detail. The mission, formally proposed in 2001 and approved in 2003, had a single primary objective: reach Pluto, photograph it and its moons, measure its atmosphere, and transmit the data home. Everything about the spacecraft's design reflected this singular purpose. It was built fast and light, with a total mass of less than 500 kilograms, so that it could be launched on the most powerful rocket available and achieve the highest velocity ever imparted to a human-made object leaving Earth. It was built cold, with no onboard heating except what its instruments required, because it would spend most of its life in regions where sunlight provides effectively no warmth. And it was built autonomous, with the intelligence to execute complex observation sequences without real-time guidance from Earth. Because at Pluto's distance, a radio signal takes nearly 5 hours to reach the spacecraft, and another 5 hours for a response to return. No human could fly the mission in real time. New Horizons had to fly itself. On January 19, 2006, at precisely 2:00 p.m. Eastern Standard Time, a Lockheed Martin Atlas V rocket lifted off from Cape Canaveral Launch Complex 41, carrying New Horizons toward the outer solar system. 58 seconds into flight, the solid rocket booster separated. 4 minutes after launch, the Centaur upper stage ignited, pushing the spacecraft faster. 9 minutes after launch, a third stage, added specifically for this mission, fired to provide the additional velocity needed to reach Jupiter within 13 months. When the final stage separated and New Horizons began its long coast toward the outer planets, it was travelling at approximately 36,000 miles per hour relative to Earth. This made New Horizons the fastest spacecraft ever launched. Previous record holders like Voyager 1 and Pioneer 10 had achieved higher velocities, but only after receiving gravity assists from multiple planets over many years. New Horizons reached its escape velocity immediately upon leaving Earth, and it continued to accelerate during a gravity assist from Jupiter in February 2007 that added another 9,000 miles per hour to its speed. By the time it passed Jupiter's orbit heading outward, New Horizons was travelling at approximately 51,000 miles per hour, fast enough to cross the distance from Earth to the Moon in about 5 hours. The spacecraft then settled into a journey that would require nearly a decade of patient waiting. Consider what those 9.5 years meant. When New Horizons launched, YouTube was less than a year old. The first iPhone would not appear for another 18 months. The global financial crisis had not yet occurred. When New Horizons reached Pluto in July 2015, the world it returned to had transformed in ways its designers could never have anticipated. Yet the spacecraft itself remained unchanged, a technological time capsule crossing the void, its systems periodically checked by mission controllers who uploaded new software to account for the evolving needs of the mission. The Pluto encounter itself lasted approximately 24 hours of close approach out of a 9.5-year mission. 24 hours to justify nearly a decade of flight. 24 hours to collect enough data to keep scientists busy for years, even decades afterward. New Horizons approached Pluto with its instruments powered and ready, executed a meticulously choreographed sequence of observations as it swept past at nearly 31,000 miles per hour, and then continued outward into the darkness, its recorders full of images and measurements that would take 16 months to fully transmit home. The images that reached Earth in the days after the flyby astonished the world. Pluto was not the dead, cratered ball of ice that some had expected. It was a geologically active world, with mountain ranges of water ice 3 kilometers high, vast plains of frozen nitrogen that showed evidence of convective circulation, and a thin but detectable atmosphere of nitrogen and methane that extended hundreds of kilometers above the surface. The heart-shaped feature that came to be known informally as Tombor Regio, named for Pluto's discoverer Clyde Tombaugh, became an icon of the mission, appearing on magazine covers and inspiring countless pieces of art. Pluto's largest moon, Charon, proved equally surprising. Rather than a simple icy ball, Charon displayed enormous canyons, strange reddish-brown deposits on its poles that turned out to be organic compounds, and evidence of past cryovolcanism. The 4 smaller moons, Nix, Hydra, Kerberos, and Styx, were revealed as irregularly shaped objects tumbling chaotically through the Plutonian system, their rotations so complex that predicting their orientations required sophisticated mathematical models, and then the encounter was over. Pluto shrank behind New Horizons like a harbour receding from a departing ship. The primary mission was complete, all objectives achieved or exceeded, full success. This was the moment when New Horizons could have ended. The engineers could have begun the process of shutting down instruments, reducing the spacecraft to minimal power mode, allowing it to drift silently outward as a monument to human achievement. Mission complete. Move on to the next project. But Alan Stern, the principal investigator who had spent nearly 3 decades fighting to get a mission to Pluto approved and built, had planned for something else. Even before launch, Stern and his team had begun looking ahead to what might come after Pluto. The spacecraft had been designed with modest fuel reserves precisely because Stern knew there might be an opportunity to visit a second target in the Kuiper Belt, if one could be found in a location that New Horizons could actually reach. Finding that target proved almost impossibly difficult. The problem was not a shortage of Kuiper Belt objects. Astronomers had discovered thousands of them by 2015. The problem was geometry. New Horizons was travelling on a fixed trajectory, and while the spacecraft carried enough hydrazine propellant to make small course corrections, it could not dramatically alter its path. Any potential target would need to be located almost exactly along the trajectory New Horizons was already following, within a narrow cone of space that the spacecraft could reach with its limited fuel reserves. The probability of a known Kuiper Belt object happening to fall within this cone was effectively 0, so the team began searching for unknown objects. In 2014, more than a year before the Pluto encounter, the Hubble Space Telescope was pointed toward the region of sky, ahead of New Horizons' projected path. Over several months, Hubble's cameras captured repeated images of the same patch of space, looking for faint points of light that moved against the fixed background of stars. Any moving object would be a potential Kuiper Belt object. If it moved at the right rate and in the right direction, it might be a reachable target. The search team, led by John Spencer and Mark Bai at the Southwest Research Institute, faced formidable odds. They were looking for objects so distant and so small that they appeared as mere pixels even in Hubble's images, and they were looking in a region of sky so densely packed with background stars that distinguishing real Kuiper Belt objects from noise required painstaking analysis of thousands of images. The computational resources necessary to process the data exceeded what the team could access, so they turned to an unconventional solution, a citizen science project called Ice Hunters, which enlisted volunteers to help identify candidate objects by examining the images manually. Even with this help, the search struggled. By early 2014, the team had found no viable targets. The window for executing a course correction maneuver was closing. If no target could be identified within the next few months, New Horizons would fly past Pluto and into empty space, its extended mission possibilities forever lost. Then, in June 2014, the search team found something. Actually, they found 3 somethings. 3 objects, designated PT-1, PT-2, and PT-3, all located along trajectories that New Horizons could potentially reach. PT-1 was the most accessible, requiring the smallest course correction and offering the earliest possible encounter date. But PT-1 was also extremely small, probably less than 20 kilometers across, and it orbited in a relatively uninteresting region of the Kuiper Belt. PT-3 was larger and scientifically more promising, but it would require a larger course correction that might leave New Horizons with insufficient fuel for proper targeting. PT-2 offered a compromise. It was estimated at roughly 30 kilometers in diameter, large enough to be scientifically interesting, and it occupied a particularly fascinating orbital location: the cold classical Kuiper Belt, a region of objects that have remained in nearly circular undisturbed orbits since the solar system's formation. Objects in the cold classical Kuiper Belt are thought to be the most pristine remnants of the primordial solar nebula, the least altered by collisions or gravitational perturbations over the past 4.5 billion years. The team selected PT2. Its formal designation was 2014 MU69, and it would later receive the name Arakoth, a Native American word meaning sky in the Powhatan language. On October 22, 2015, less than 4 months after the Pluto encounter, New Horizons executed the first of 4 course correction burns that would aim it toward Arakoth. The maneuver consumed precious fuel, but it set the spacecraft on a path toward a rendezvous more than 3 years away. Those 3 years were not idle. Even as New Horizons coasted toward its next target, its instruments remained active, collecting data about the environment of the Kuiper Belt itself. The spacecraft measured the density of dust particles in the region, counting the tiny impacts of micrometeoroids against a dedicated detector. It monitored the solar wind, the stream of charged particles flowing outward from the sun, measuring how its properties changed at these extreme distances. It observed dozens of other Kuiper Belt objects from afar, measuring their colours, their sizes, their rotations, building up a statistical portrait of the population as a whole. And the team on Earth used those 3 years to learn as much as possible about Arakoth before arrival. Knowing what you are approaching matters enormously when you have only one chance to get the observations right. Ground-based telescopes tracked the object, refining estimates of its orbit and size. When Arakoth passed in front of distant stars, a phenomenon called a stellar occultation, teams of observers positioned across South America and the Pacific captured the brief shadow, using the duration and shape of the occultation to map the object's silhouette with astonishing precision. What they found was strange. Arakoth did not appear to be a simple spherical or ellipsoidal body. The occultation data suggested something elongated, possibly bilobed, perhaps even binary. 2 objects touching, or nearly touching, orbiting each other so closely that they appeared as one. This was tantalizing. Contact binaries, objects formed when 2 separate bodies gently collide and stick together, had been theorized but never observed up close. If Arakoth was indeed a contact binary, New Horizons would be witnessing something that had never been seen before. On December 31, 2018, mission controllers at the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, waited in nervous anticipation. New Horizons was approaching Arakoth at a relative velocity of about 32,000 miles per hour. At closest approach, scheduled for 12:33 a.m. Eastern Time on January 1, 2019, the spacecraft would pass within 2,200 miles of the object's surface, 3 times closer than it had approached Pluto. The encounter would be fast. Arakoth would sweep through New Horizons' field of view in a matter of hours, and every second of that window had been programmed with specific observations months in advance. The team could not monitor the flyby in real time. At Arakoth's distance, more than 4 billion miles from Earth, radio signals took 6 hours and 8 minutes to make the journey at the speed of a light. When the closest approach occurred, mission controllers would not receive confirmation for more than 6 hours, and the spacecraft itself was out of contact during the critical observation window, its antenna pointed at Arakoth rather than Earth, its onboard computers executing the pre-programmed sequence with no human oversight. At 10:29 a.m. Eastern Time on January 1, 2019, the first signal arrived. New Horizons was alive. It had survived the encounter. The data was being collected as planned. The first images trickled in over the following days, initially low-resolution previews sent quickly to confirm success, followed by progressively higher-resolution data that would take months to transmit completely. What emerged from those images exceeded every expectation. Arakoth was indeed a contact binary, but it was not 2 roughly spherical objects touching like a cosmic snowman. It was 2 distinctly flattened lobes, one larger and one smaller, joined at a narrow neck. The overall shape resembled nothing so much as a reddish snowman that had been partially melted and then refrozen, or perhaps a lumpy peanut, or a crude figurine made of clay by an inexperienced sculptor. The larger lobe, informally named Ultima, measured approximately 22 kilometers across. The smaller lobe, Thule, was roughly 14 kilometres. Together they formed an object about 36 kilometres long, tumbling slowly through space with a rotation period of roughly 15 hours. The colour was striking. Arakoth appeared reddish-brown across its entire surface, the result of organic compounds called tholins that form when ultraviolet light from the sun processes simpler molecules like methane and nitrogen over billions of years. These tholins are common in the outer solar system. Pluto has them. Titan has them. But on Arakoth they coat the surface uniformly, testifying to the object's extreme age and lack of recent geological activity. Most remarkably, Arakoth showed almost no impact craters. Pluto had been covered with craters of all sizes, as had Charon and the smaller moons. But Arakoth's surface was smooth, marked primarily by gentle depressions and subtle albedo variations rather than the sharp-rimmed bowls that mark most airless bodies. This smoothness was not evidence of geological resurfacing. Arakoth has no internal heat, no cryovolcanism, no mechanism to erase craters once they form. Instead, the lack of craters suggested something profound about the Kuiper Belt itself, that collisions out there are far less frequent than astronomers had assumed. The cold classical Kuiper Belt, it seemed, was a remarkably peaceful place. The objects there drift through the void in their ancient orbits, rarely encountering one another, preserved in nearly the same state they achieved when they first formed 4.5 billion years ago. Arakoth was not merely old, it was unchanged, a genuine relic of the solar system's birth, frozen in time as surely as an insect in amber. But the most important discovery about Arakoth concerned its formation. The two lobes, Ultima and Thule, had clearly once been separate objects that came together. The question was how. Two main theories existed for how contact binaries form. In the first, violent collisions fragment larger bodies into smaller pieces that later reaccumulate chaotically, smashing together at high speeds. In the second, gentler process called gravitational collapse, clumps of material in the primordial solar nebula slowly settle together under their own mutual gravity, drifting toward one another at walking speed until they touch and stick. The evidence from Arakoth was unambiguous. The two lobes showed no signs of high-speed impact damage. They were aligned with each other, their equators matching, suggesting they had formed from the same rotating cloud of material. The neck where they joined showed no fractures, no compression ridges, none of the features that would result from a violent collision. Ultima and Thule had drifted together as gently as two soap bubbles merging, perhaps at velocities of a few meters per second, no faster than a person walking briskly. This was direct evidence for a formation mechanism that had been theorized but never observed. Planetary scientists call it pebble accretion, or streaming instability, depending on the specific model, but the basic idea is the same. In the earliest phase of solar system formation, before the planets existed, particles in the disk of gas and dust surrounding the young sun could clump together through gravitational attraction rather than collisions. These clumps, these primordial planetesimals, were the seeds from which everything else grew. Arakoth was such a seed, preserved untouched for 4.5 billion years. The implications rippled through planetary science. If contact binaries like Arakoth are common in the Kuiper Belt, and other observations suggested they might be, then the gentle accretion model of planetesimal formation must be correct. The building blocks of planets were not assembled through violence but through patience, particles drifting together over millions of years, gravity doing the work that collisions could not. This insight applies not just to our solar system, but to every planetary system around every star in the galaxy. New Horizons had provided evidence about how planets form everywhere in the universe. After the Arakoth encounter, New Horizons continued outward. There was no choice in the matter. The spacecraft had no brakes, no way to slow down, no mechanism to reverse its course. It would continue on its current trajectory until something stopped it, and in the near vacuum of the outer solar system nothing would. The probe that had succeeded too well was now travelling beyond the region, where any known objects lay in its path. But travelling through a region is not the same as having nothing to observe. The Kuiper Belt is not empty, it is merely sparse, and New Horizons, designed from the beginning to study this environment, continued to operate its instruments, continued to collect data, continued to transmit discoveries back to Earth. The spacecraft's dust counter, called the Student Dust Counter, because it was designed and built by graduate students at the University of Colorado, recorded the rate of tiny particle impacts as New Horizons moved through the belt. These particles, micrometeoroids ranging in size from smoke particles to grains of sand, are the debris from collisions between larger Kuiper Belt objects, and their density tells scientists about the history and dynamics of the region. What the counter found surprised everyone. The dust density did not decline as expected after Arakoth. Standard models predicted that the Kuiper Belt would thin out rapidly beyond about 50 astronomical units from the Sun, the dust density dropping as the population of source objects decreased. But the student dust counter continued to register impacts at rates higher than predicted, suggesting that the Kuiper Belt extends farther than thought, or that some other source of dust exists in the outer solar system that astronomers had not accounted for. Recent data, transmitted in 2023 and still being analysed, suggests the dust density may actually be increasing as New Horizons travels outward. This is genuinely anomalous. If confirmed, it could indicate the presence of a more distant population of objects beyond the classical Kuiper Belt, perhaps the inner edge of the hypothetical Oort cloud, the vast spherical shell of comets that may surround the solar system at distances of thousands or tens of thousands of astronomical units. No spacecraft has ever detected direct evidence of the Oort cloud. New Horizons may be providing the first hints. The spacecraft also carries an instrument called SWAP, the Solar Wind Around Pluto detector, which measures the properties of the solar wind at these extreme distances. The solar wind weakens as it travels outward from the Sun, spreading across an ever larger volume of space. By the time it reaches New Horizons, nearly 60 astronomical units from the Sun, the wind has become a thin trickle, barely detectable above the background of galactic cosmic rays. But SWAP continues to measure it, tracking the variations in wind speed and density that reveal the Sun's activity even at these remote distances. In 2021, SWAP detected something unexpected, evidence that the solar wind was beginning to slow more dramatically than models predicted, suggesting that New Horizons was approaching the region where the outflowing solar wind begins to pile up against the incoming pressure of interstellar space. This boundary region, called the Helios sheath, marks the beginning of the end of the Sun's influence. Voyager 1 crossed into the Helios sheath in 2004 and exited into interstellar space in 2012. Voyager 2 followed in 2018. New Horizons is travelling in a different direction, and its measurements provide a new perspective on this critical boundary, revealing how its properties vary across different regions of space. New Horizons cameras remain operational, though they are used sparingly now to conserve power. When scientifically justified, the spacecraft can be commanded to photograph distant Kuiper Belt objects from unique vantage points that ground-based telescopes cannot achieve. These observations, called phase-angle measurements, capture how objects reflect light at extreme angles, revealing information about surface texture and composition that cannot be determined any other way. Since the Arakoth flybeast, New Horizons has photographed dozens of distant Kuiper Belt objects from its unique perspective, building a database of observations that complements and extends what can be seen from Earth. But every observation costs power, and power is the one resource that New Horizons cannot replenish. The spacecraft runs on a single radioisotope thermoelectric generator, a device that converts the heat from decaying plutonium-238 into electrical power. When New Horizons launched in 2006, its RTG produced approximately 245 watts of electricity, roughly enough to power a few incandescent light bulbs. Plutonium-238 has a half-life of 87.7 years, meaning that every 87.7 years, half of the remaining plutonium decays into inert materials that produce no heat. The RTG's power output drops accordingly, declining by about 4 watts per year. By 2023, the RTG was producing less than 200 watts. By 2030, it will drop below 175 watts. By the late 2030s, the power output will become insufficient to operate the spacecraft's transmitter at full strength, and sometime in the early 2040s, the RTG will no longer produce enough electricity to keep the spacecraft's critical systems functional. New Horizons will go silent. The mission team at Johns Hopkins Applied Physics Laboratory knows this. They have been planning for it since before launch. As the power declines, they will progressively shut down instruments, reducing the spacecraft's science capability to extend its operational lifetime as long as possible. The dust counter will likely be the last to go, its power requirements the lowest of any instrument, its measurements the most valuable for understanding the environment at the very edge of the Sun's domain. Alice Bowman, the mission operations manager, has overseen New Horizons since before its launch. She has spent nearly 2 decades watching over this small machine as it crossed the solar system, and she will likely be watching when it finally falls silent. The spacecraft, she has said, has become like an old friend, reliable and steady, sending its signals home across a gulf of space that grows a little larger every day. When those signals stop, a part of her will go silent too. But that silence is still years away. Right now, in this moment, New Horizons continues its journey. It is currently more than 58 astronomical units from the Sun, farther than any functioning spacecraft except the Voyagers, which launched decades earlier. It is travelling outward at approximately 33,000 miles per hour relative to the Sun, adding about 3 astronomical units to its distance every year. By the end of 2025, it will have passed the 60 astronomical unit mark, a distance so vast that light itself takes more than 8 hours to cross it. What lies ahead in that darkness is largely unknown. The instruments can still detect things. The dust counter can still register impacts. The plasma sensors can still measure the solar wind. The cameras can still photograph distant objects if commanded. Every measurement adds to our knowledge of a region that no previous spacecraft has explored, that no telescope can observe in detail, that exists beyond the boundaries of every map humanity has ever made. The spacecraft that succeeded too well continues to succeed, even as its power fades, even as its systems gradually shut down, even as the darkness closes in around it. New Horizons was built for one flyby. It has now completed 2, and it continues to make discoveries years after its primary mission ended. The engineers who designed it could not have known how long it would last or how much it would find. They built a machine to photograph Pluto, and that machine became something more, a pioneer, a pathfinder, a lonely sentinel pushing outward into the unknown. In the Kuiper Belt, there are no roads, no landmarks, no way to navigate except by the stars themselves. New Horizons travels this emptiness alone, its antenna always pointed homeward, its transmitter always ready to send whatever it finds back to the small blue world that sent it forth. The journey continues, the discoveries accumulate, and somewhere in the darkness ahead, things that no one has ever seen await a spacecraft that refuses to stop looking. The Kuiper Belt through which New Horizons travels is not the asteroid belt of science fiction. There are no dense fields of tumbling rocks requiring careful navigation, no dramatic swerves to avoid collision, no sense of crowding or danger. The reality is almost the opposite. The Kuiper Belt is so vast and its objects so widely scattered that a spacecraft could travel through it for centuries without coming within 1,000,000 miles of anything larger than a grain of sand. The belt contains an estimated trillion objects larger than a kilometre in diameter, but those trillion objects are distributed across a region so enormous that the average distance between them measures in the tens of millions of miles. If you were standing on one Kuiper Belt object and looking for the nearest neighbour, you would see nothing but stars. The neighbour would be invisible, lost in the darkness, too small and too far to register against the background of space. This emptiness shapes everything about how we explore the outer solar system. We cannot wander through the Kuiper Belt hoping to stumble across something interesting. We must choose our targets years in advance, calculate trajectories with exquisite precision, and commit to flybys that cannot be altered once the spacecraft is underway. When the New Horizons team began searching for a post-Pluto target in 2014, they faced constraints that would have seemed absurd to explorers of any previous century. They needed an object that the spacecraft could actually reach with its remaining fuel. They needed that object to be large enough and bright enough for the spacecraft's cameras to capture meaningful images during a high-speed flyby. And they needed to find it within a search corridor so narrow that the probability of any suitable object existing within it was genuinely uncertain. The search began with ground-based telescopes. The team used the Subaru telescope on Mauna Kea in Hawaii, one of the largest optical telescopes in the world, to scan the region of sky where potential targets might be found. They also enlisted the Hubble Space Telescope, still humanity's sharpest eye on the universe despite its age. The search corridor was pitilessly narrow. New Horizons was travelling so fast and had so little fuel remaining that it could only alter its trajectory by about 1 degree. Any target would need to lie almost directly in the spacecraft's path, a needle in a cosmic haystack measured in billions of cubic miles. The ground-based search found several candidates, but most were either too faint, too far off the spacecraft's trajectory, or too small to be worth the fuel expenditure required to reach them. The Hubble search proved more fruitful. In June 2014, the Space Telescope identified 3 potential targets within the reachable corridor. 2 were marginal, requiring trajectory changes that would consume most of the spacecraft's remaining hydrazine fuel. The third was better positioned but still uncertain. Then, in August 2014, Hubble found something different. The object bore the prosaic designation 11-0013Y. It was small, perhaps 20 to 30 kilometers across based on its brightness, and it was positioned almost perfectly along the spacecraft's extended trajectory. Reaching it would require only a modest fuel expenditure, leaving reserves for potential future maneuvers. The orbital mechanics aligned in ways that the mission planners had barely dared hope. If New Horizons performed a series of small engine burns in the weeks following the Pluto flyby, it could intercept this object on January 1st, 2019, arriving at the new decade in the most distant rendezvous ever attempted. The team announced the discovery with cautious excitement. The object received the official Minor Planet Center designation 2014 MU69. Informally, the team began referring to it simply as MU69, 2 letters and 2 numbers that would eventually become one of the most famous designations in planetary science. But the discovery was only the beginning. They had found a target. Now they needed to characterize it well enough to plan a flyby that would occur more than 4 years in the future. What followed was one of the most challenging observation campaigns in the history of planetary astronomy. MU69 was tiny, faint, and so distant that it moved almost imperceptibly against the background stars. Ground-based telescopes could barely detect it. Even Hubble struggled to resolve anything beyond a point of light. The team needed to know the object's exact position to program New Horizons' approach. But more than that, they needed to know if MU69 had any features that might endanger the spacecraft. A moon orbiting at hazardous distance, a ring system that might contain debris, any unexpected characteristic that could turn a triumphant flyby into a silent catastrophe. The solution came from an ancient technique applied to an ultra-modern problem: stellar occultation. When a solar system object passes directly between Earth and a distant star, the star briefly disappears, occulted by the intervening body. By precisely timing this disappearance from multiple locations on Earth, astronomers can determine the object's size, shape, and position with remarkable accuracy. The technique works because starlight acts as a near-perfect point source. When an object blocks that light, it casts a shadow on Earth, and observers within that shadow see the star vanish. For MU69, the challenge was extreme. The object was so small and so distant that its shadow would be only about 30 kilometers wide, racing across the Earth's surface at more than a kilometer per second. Observers would have less than a second to detect the occultation. The shadow's path could not be predicted with perfect accuracy because MU69's orbit was not known precisely enough, and the events were visible only from extremely remote locations, requiring expedition-style campaigns to place telescopes in the shadow's predicted path. The New Horizons team organised 3 major occultation campaigns. The first occurred in June 2017, with 24 portable telescopes deployed along a line in Argentina. Clouds interfered with some observations, but enough telescopes recorded data to confirm MU69's general size and position. The second campaign occurred weeks later, with observers positioned along a line in Patagonia. This time, clear skies allowed multiple successful observations, revealing something unexpected. The occultation profile suggested that MU69 might not be a single object. The shadow showed a double-lobed signature, as if 2 objects were closely orbiting each other, or were physically touching. The third campaign targeted the most precise prediction yet, positioning observers along a narrow corridor in Senegal. Colomer, a Sophia aircraft carrying a specialized telescope, flew through the shadow's predicted path at 40,000 feet, above the distorting effects of most of Earth's atmosphere. The data from this campaign confirmed the double-lobed structure and provided the most accurate position fix yet achieved. By late 2018, the team had assembled a portrait of MU69 that was simultaneously detailed and mysterious. The object appeared to be what planetary scientists call a contact binary, 2 separate bodies that had gently collided and stuck together, forming a single object shaped roughly like a snowman or bowling pin. The larger lobe was perhaps 20 kilometers across, the smaller lobe perhaps 14 kilometers. The two appeared to be touching at a narrow neck. This shape had profound implications. A contact binary forms when two objects approach each other so slowly that they touch rather than collide, merging rather than shattering. For this to happen in the Kuiper Belt, where orbital velocities are measured in hundreds of meters per second, the two lobes must have originated very close together, probably forming from the same cloud of dust and gas billions of years ago, spiralling slowly toward each other over eons until they finally met. If this interpretation was correct, MU69 was not just a Kuiper Belt object. It was a fossil, a preserved fragment of the solar system's earliest days, a record of how planets begin to form from the dust that swirls around newborn stars. New Horizons' closest approach occurred at 12:33 a.m. Eastern Time on January 1st, 2019, with the spacecraft passing within 1,300 kilometers of MU69's surface. This was nearly 3 times closer than the Pluto flyby, a distance chosen to maximize the resolution of the cameras and spectrometers, while minimizing the risk of collision with any undiscovered debris. At the moment of closest approach, the spacecraft was 4.1 billion miles from Earth, so far that radio signals took 6 hours and 8 minutes to cross the Gulf. No one on Earth knew whether the flyby had succeeded until the spacecraft emerged from behind MU69 and sent its first status beacon back home. The beacon arrived at 10:29 a.m. on New Year's Day. New Horizons had survived, but the images that followed over the subsequent days transformed MU69 from a scientific target into an icon. The object was indeed a contact binary, but its shape was stranger and more beautiful than the occultation data had suggested. The larger lobe was not spherical but flattened, like a hamburger patty or a thick pancake, measuring roughly 36 kilometers across but only about 6 kilometers thick. The smaller lobe was similarly flattened but more rounded, roughly 15 kilometers in diameter. The two were joined at a bright collar of material that appeared relatively smooth compared to the rough, cratered surfaces of the lobes themselves. The overall impression was less snowman than cosmic walnut, 2 flattened lobes pressed together and frozen in place for billions of years. The team initially nicknamed the object Ultima Thule, a term from medieval geography meaning beyond the known world. This name later generated controversy due to its historical associations with Nazi mysticism, and in November 2019, the International Astronomical Union officially named the object Arakoth, a word meaning sky in the Powhatan language, honouring the indigenous people whose traditional territories include the region where the Johns Hopkins Applied Physics Laboratory is located. The images of Arakoth revealed a surface unlike anything previously photographed in the solar system. It was remarkably uniform in colour, displaying a dark reddish-brown hue across both lobes and the connecting neck. This uniformity suggested that the entire surface had been processed by the same external forces, probably billions of years of cosmic ray bombardment and solar ultraviolet radiation that had transformed the original surface materials into the complex organic molecules called tholins. The colour confirmed what spectral data had hinted. Arakoth's surface was rich in organic compounds, the carbon-based molecules that form the building blocks of life. But the most striking feature of Arakoth was what it lacked: large impact craters. The surfaces of inner solar system bodies are typically battered landscapes, scarred by billions of years of bombardment. The Moon is cratered from pole to pole. Mercury's surface is a record of violence. Mars carries the wounds of 4 billion years of impacts. Even distant Pluto showed a mix of ancient cratered terrain and younger resurfaced regions. Arakoth should have looked similar. It has been orbiting in the Kuiper Belt for the full age of the solar system, exposed to the same population of impactors that cratered everything else. Instead, Arakoth's surface was remarkably smooth. The team identified a few small craters, but nothing larger than about a kilometre in diameter, and the overall crater density was far lower than expected. This unexpected smoothness demanded explanation. Either the Kuiper Belt contains far fewer small impactors than models predicted, or some process has erased Arakoth's craters over time, or both. The current leading hypothesis combines both factors. The Kuiper Belt appears to be surprisingly depleted in objects smaller than about a kilometre, a finding that Arakoth's smooth surface helped reveal. Without a population of small impactors, large craters cannot form frequently, and the surface remains relatively pristine. Additionally, the weak gravity of such a small object means that even modest impacts can eject material that escapes entirely rather than falling back to create secondary craters. The material simply drifts away into space, leaving the surface cleaner than it would be on a larger body. Arakoth also provided the first direct evidence for how planets form in their earlier stages. The standard model of planetary formation holds that planets grow from the gradual accumulation of smaller bodies. Dust grains stick together to form pebbles. Pebbles accumulate into boulders. Boulders merge into planetesimals kilometers across. Planetesimals collide and grow into planetary embryos, and embryos eventually become planets. This hierarchical process, building larger structures from smaller components, has been the dominant paradigm for decades. But there has always been a problem. Computer simulations show that the intermediate steps are surprisingly difficult. Pebbles and boulders collide at velocities that should shatter them rather than merge them. Objects in this size range experience aerodynamic drag in the primordial gas disk that causes them to spiral inward toward the Sun, rather than remaining in place to accumulate. Getting from dust grains to planetesimals seem to require improbably gentle collisions and improbably long timescales. Arakoth suggests a different path. The object's two lobes appear to have formed separately and then merged so gently that neither was deformed by the collision. This gentle merger is exactly what would be expected if the lobes formed from the same gravitationally collapsing cloud of pebbles, drawing together slowly over thousands or millions of years as the cloud contracted. Rather than growing hierarchically through violent collisions, Arakoth may have formed directly from a pebble cloud, bypassing the problematic intermediate stages entirely. This process, called streaming instability, occurs when small particles in a gas disk clump together due to a feedback loop between the particles and the gas. The clumps become dense enough to collapse gravitationally, forming planetesimals directly without the need for intermediate collisions. Arakoth's shape, composition, and remarkably undisturbed structure all support this model. The object appears to be exactly what streaming instability would produce. Two dense clumps that formed close together and merged gently into a single body. If this interpretation is correct, Arakoth is not merely an interesting outer solar system object. It is a witness to the birth of the planets, a fragment of the process that formed Earth itself, preserved in frozen perfection at the outer edge of the Sun's domain. Every planet in our solar system, including the one we live on, may have begun as something similar to Arakoth, pebble clouds collapsing under their own gravity, merging gently in the darkness between the stars. The Arakoth flyby produced more than 6 gigabytes of data, far more than could be transmitted home in the hours immediately following the encounter. The slow trickle of information continued for nearly 2 years, with the spacecraft sending data at rates as low as 1 kilobit per second, slower than the earliest dial-up modems of the 1990s. Each image, each spectrum, each measurement of particles and fields crossed the void at the speed of light and then crept through the data link at a pace that tested the patience of scientists who had waited years for this moment. The final Arakoth data reached Earth in September 2020. By then, New Horizons had travelled another 300 million miles, pushing ever deeper into the Kuiper Belt, leaving Arakoth behind as it had left Pluto behind before it. The spacecraft had accomplished something unprecedented. The first exploration of 2 completely different Kuiper Belt objects, revealing 2 worlds as different from each other as either was different from anything closer to the Sun. Pluto was geologically complex, with nitrogen glaciers and methane mountains and a thin but detectable atmosphere. Arakoth was geologically simple, a primordial snowman frozen in the moment of its formation, unchanged since the solar system was young. Together they demonstrated that the Kuiper Belt is not a monotonous collection of similar objects, but a diverse population spanning the full range of sizes, compositions and histories. The belt contains worlds and it contains fossils. It contains objects large enough to differentiate into layers and objects small enough to preserve their original structure. It contains the full 4 billion year history of the outer solar system, written in ice and rock and organic molecules, waiting to be read by spacecraft patient enough to make the journey. But New Horizons' story did not end with Arakoth. The spacecraft's trajectory carries it steadily outward, and while no third flyby is currently planned, the instruments continue to function. The antenna continues to point homeward, and the data continues to flow. The mission has entered what the team calls its extended mission phase, a period of ongoing observation and discovery that will continue until the RTG can no longer supply sufficient power. What the spacecraft observes during this extended phase is in some ways more valuable than what it observed during the flybys themselves. New Horizons carries the Student Dust Counter, that small instrument built by University of Colorado undergraduates that has been registering particle impacts since before the spacecraft reached Jupiter. The counter consists of thin plastic films stretched across a detector, recording the electrical signal generated when microscopic particles punch through the film. Each impact damages the detector slightly, but the cumulative damage has been far less than feared. The instrument continues to function decades after launch, providing the only direct measurements of dust density in the outer solar system. The dust measurements have revealed something unexpected. Models predicted that dust density would decline steadily with distance from the Sun, following a smooth curve from the relatively dusty inner solar system to the nearly empty outer reaches. The actual measurements show a different pattern. The decline is not smooth. There are regions where dust density is higher than expected and regions where it is lower. The Kuiper Belt appears to have structure, variations in dust density that map to variations in the population of larger objects that produce the dust through collisions. This finding matters because dust is the exhaust of planetary systems. When objects collide, they produce debris. When comets sublimate, they release particles. When asteroids and Kuiper Belt objects grind against each other over billions of years, they generate the fine powder that drifts through interplanetary space. By mapping the dust, New Horizons is mapping the violence and activity of the outer solar system, revealing where collisions happen and where objects accumulate. The dust counter has also detected something more intriguing, evidence that the Kuiper Belt may extend far beyond where traditional models placed its outer edge. The classical Kuiper Belt was thought to end at about 50 astronomical units, beyond which the density of objects drops precipitously. But the dust measurements show elevated densities extending past 60 astronomical units, suggesting that the scattered disk population, those objects flung onto eccentric orbits by ancient encounters with Neptune, extends far deeper into space than previously recognized. Meanwhile, the plasma instruments continue to measure the solar wind, tracking its gradual weakening as New Horizons travels outward. The solar wind is a stream of charged particles flowing constantly outward from the Sun, a river of protons and electrons that fills the entire solar system. Near Earth, the wind blows at roughly 400 kilometers per second and carries enough particles to create measurable effects. Auroras, magnetospheric compression, the tails of comets always pointing away from the Sun. As distance from the Sun increases, the wind spreads and weakens, its energy distributed across an ever larger sphere. New Horizons plasma measurements are complementing those from Voyager 1 and Voyager 2, which crossed into interstellar space in 2012 and 2018 respectively. The Voyagers are decades ahead of New Horizons, already beyond the heliopause, the boundary where the solar wind finally slows to a stop against the pressure of interstellar space. New Horizons is still deep within the heliosphere, the bubble of solar influence that extends perhaps 120 astronomical units from the Sun. But the spacecraft's trajectory is different from the Voyager's. It is travelling in a different direction, through a different sector of the heliosphere, providing measurements that reveal how the bubble varies from place to place. The heliosphere is not a perfect sphere. It is distorted by the Sun's motion through the local interstellar medium, compressed on the leading edge and stretched into a long tail on the trailing edge. The Voyagers exited through the nose of this structure. New Horizons is travelling more toward the flank, where the bubble's characteristics may differ significantly. The data the spacecraft is collecting will help scientists understand the three-dimensional structure of our star's domain, the shape of the vessel that carries us through the galaxy. And then there are the cameras. LORRI, the long-range reconnaissance imager that captured the iconic images of Pluto's heart and Arakoth's snowman shape, remains fully functional. The telescope can still photograph distant objects if commanded, still resolve details that no Earth-based telescope can see. The team has used LORRI to observe several other Kuiper Belt objects from a distance, capturing images that reveal rotation rates, approximate sizes, and sometimes the presence of moons or binary companions. These distant observations cannot match the resolution of a close flyby, but they provide information unavailable from any other source. The viewing geometry from New Horizons is unique. The spacecraft sees Kuiper Belt objects at phase angles impossible from Earth, illuminated from directions that reveal surface features invisible in the constant full sun lighting we observe from our home planet. Some objects have displayed unexpected brightness variations, suggesting irregular shapes or albedo patterns. Others have shown hints of companions, multiple objects where single objects were expected. The cameras have also looked backward, toward the inner solar system, capturing images of distant planets seen from perspectives no human eye has ever witnessed. Neptune appears as a pale blue dot. Uranus is a tiny green speck. Earth, when the viewing geometry allows, is utterly invisible, lost in the glare of the sun, a reminder that our world is nothing special when viewed from the outer solar system. Perhaps most poignantly, the cameras have photographed stars, not for navigation or science, but for perspective. The starfield looks identical from New Horizons' position and from Earth's surface. At interstellar scales, even a journey of 58 astronomical units represents essentially no change in viewing angle. The spacecraft has travelled so far that light takes 8 hours to reach it, yet the sky looks the same. This sameness is humbling. It reveals how far we have to go before our explorations register on cosmic scales, how small even our most ambitious journeys appear against the backdrop of the galaxy. And yet those journeys matter. Every measurement New Horizons makes, every particle impact it records, every distant photograph it captures, adds to humanity's understanding of the universe we inhabit. The spacecraft carries our curiosity outward, extending our senses into regions we cannot otherwise perceive, reporting back what it finds until the power finally fails and the transmissions cease. The power question haunts every decision the team makes now. New Horizons launched with a single radioisotope thermoelectric generator, a cylinder containing 10.5 kilograms of plutonium dioxide. The heat of its radioactive decay converted into electricity by an array of thermocouples. At launch, this generator produced roughly 245 watts of electrical power, enough to illuminate 3 standard light bulbs. By the Pluto encounter, decay had reduced this output to around 202 watts. Today the generator produces less than 190 watts, and the decline continues at an inexorable rate of approximately 4 watts per year. Plutonium-238 has a half-life of 87.7 years, which means the fuel itself will remain radioactive for centuries, but the thermocouples that convert heat to electricity degrade faster than the plutonium decays. The efficiency of the conversion drops as the spacecraft ages. The combination of declining heat output and declining conversion efficiency creates a power curve that steepens over time, each year bringing a larger percentage loss than the year before. The engineers know exactly when the power will drop below the level needed to operate the spacecraft's core systems. They know which instruments will have to be turned off first, which functions will be sacrificed to keep the transmitter and basic computers running a little longer. They have planned for this decline since before launch, building in power margins and operational flexibility, but the planning cannot change the physics. The plutonium runs down, the power fades, the spacecraft eventually falls silent. This is not failure. This is the universe asserting its rules. New Horizons was designed to operate for years, perhaps a decade beyond its primary mission, and it has exceeded every expectation. The spacecraft has survived longer than many predicted, operated more efficiently than specifications required, and returned more data than originally planned. But RTGs do not last forever. Nothing does. The question is not whether New Horizons will die, but what it will accomplish in the time remaining. The mission team has developed a strategy they call hibernation cycling. During periods when no specific observations are planned, the spacecraft enters a deep sleep state, with most systems powered down and only essential functions running. This reduces power consumption by more than half, preserving the precious wattage for moments when it matters. The spacecraft awakens periodically to check its own health, transmit stored data, and receive new commands. Then it sleeps again, waiting for the next observation opportunity, the next distant Kuiper Belt object to photograph, the next measurement campaign to execute. This cycling allows the team to stretch the available power over more years, to extend the mission further into the outer solar system than continuous operations would permit. Every watt saved during hibernation is a watt available for science when the spacecraft awakens. The strategy requires extraordinary discipline. Ground controllers must resist the temptation to command continuous observations, to use the spacecraft every day simply because they can. They must accept long periods of silence, weeks or months when New Horizons drifts outward without human contact, trusting that the onboard systems will maintain themselves, that the spacecraft will awaken on schedule, that nothing critical will fail in the darkness. This trust has been earned through years of flawless performance, through engineering excellence that translated design specifications into actual reliability. But trust is not certainty. Every hibernation period carries risk. Every awakening is a small miracle. The distance compounds every problem. At 58 astronomical units from the Sun, light takes approximately 8 hours to travel from New Horizons to Earth. A command sent from Mission Control does not reach the spacecraft until more than 8 hours later. A response does not return until more than 8 hours after that. 16 hours pass between asking a question and receiving an answer. If something goes wrong, if an anomaly occurs or a system behaves unexpectedly, the team cannot respond in real time. They must diagnose the problem through telemetry that is already hours old, devise a solution, transmit commands, and wait another 8 hours to see if the fix worked. Emergency procedures must be autonomous, built into the spacecraft's own programming, executed without human intervention. The spacecraft must be capable of detecting problems and responding to them faster than any message could travel from Earth. This autonomy is another form of trust. The engineers wrote software to handle contingencies, to respond to failures, to keep the spacecraft safe when no one is listening. But software cannot anticipate every possibility. The outer solar system may contain hazards no one predicted, conditions no model accurately captured. The spacecraft carries only the knowledge it launched with, updated periodically through uploaded commands, but fundamentally limited by human imagination at the time of design. New Horizons is increasingly alone out there, a small machine carrying human intentions into regions that have never seen human technology, operating on instructions written years ago by people who could only guess at what conditions the spacecraft would encounter. The signals themselves have become precious commodities. New Horizons transmits data at roughly 1 to 2 kilobits per second, depending on the configuration of the deep space network antennas receiving the signal. This is roughly equivalent to the speed of a 1990s dial-up modem, the kind that screeched and burbled while connecting to early internet services. At this rate, transmitting a single high-resolution LORRI image takes hours. Transmitting the complete dataset from a major observation campaign takes weeks or months. The spacecraft's solid-state recorders can store roughly 8 gigabytes of data, an amount that would fill a cheap USB drive, but that data trickles back to Earth at rates that make patience a mandatory virtue. The deep space network itself becomes a limiting factor. The network consists of 3 antenna complexes positioned around the globe in California, Spain, and Australia, arranged so that at least one complex has line of sight to any point in the sky at any given time. These antennas support dozens of spacecraft, from Mars rovers to distant probes to Earth-orbiting satellites requiring backup communication. Scheduling time on the large antennas, the 70-meter dishes that can receive the weakest signals from the greatest distances, requires negotiation and prioritization. New Horizons is one client among many, and as it recedes further from the Sun, its signals weaken, requiring longer antenna time to extract the same amount of data. The spacecraft competes for attention with missions that are louder, closer, more immediately productive. This competition will only intensify as power drops and signals fade, and yet the mission continues to find things worth transmitting. The Kuiper Belt observations from distant flybys have revealed surprises that justify every hour of antenna time. One object observed by LORRI showed a rotation period far shorter than expected, spinning fast enough that its shape should be distorted by centrifugal force. Another displayed brightness variations suggesting an extremely elongated shape, a cigar or pancake, rather than the roughly spherical form that gravitational self-rounding would predict for such a size. A third appeared to be not one object but 2, a contact binary or closely orbiting pair, their combined light curve revealing the dance of components no one knew existed. These observations are necessarily limited. LORRI was designed for close-up work, for resolving features on Pluto and its moons from distances measured in thousands of kilometers. Photographing Kuiper Belt objects from millions of kilometers produces images where the targets are barely more than points of light. Their shapes and surfaces inferred from brightness changes rather than directly seen. But inference is still data. The brightness curves that reveal rotation and shape would be impossible to obtain from Earth, where the distant Kuiper Belt objects appear as motionless points against the starfield. They're like too faint and stable to reveal internal properties. New Horizons' unique viewing geometry, its position deep within the belt, allows observations that ground-based telescopes cannot replicate. The spacecraft has also contributed to understanding of objects that will never receive close visits. Most Kuiper Belt objects will remain unvisited for generations, their orbits and properties known only through telescopic observation. The characterization work New Horizons performs, the rotation rates and shapes and binary frequencies it measures, build statistical knowledge about the population as a whole. Each observation is a single data point, but collected data points become distributions, and distributions reveal formation processes, evolutionary histories, the physics that shaped the outer solar system during its youth. New Horizons is conducting a census as it travels, counting and characterizing the inhabitants of a region that spans 1 billion kilometers. The trajectory itself opens possibilities for additional flybys. After Arakoth, mission planners began searching for other Kuiper Belt objects that might pass close enough to the spacecraft's path to permit detailed observation. The search is severely constrained. New Horizons cannot change direction significantly. The fuel remaining in its hydrazine thrusters is sufficient only for minor course corrections. The delicate adjustments needed to maintain proper Earth pointing for communication or to observe specific targets. A major trajectory change, the kind that would send the spacecraft toward a distant object far from its current path, is simply impossible. The propellant does not exist. The spacecraft must find targets of opportunity, objects that happen to lie near the trajectory it is already following. This limitation reduces the search to a needle in a haystack problem. The Kuiper Belt contains billions of objects, but space is vast and encounters are rare. Most objects orbit in the classical Kuiper Belt, the main concentration of bodies between roughly 40 and 50 astronomical units from the Sun. New Horizons passed through this region years ago, and now travels beyond it, into the scattered disk and eventually toward the termination shock of the solar wind. The density of objects decreases as distance increases. The probability of finding a reachable target diminishes with each passing month. The search uses the most powerful telescopes on Earth. The Subaru telescope on Mauna Kea, with its 8.2-meter mirror and wide-field camera, can detect objects as faint as 27th magnitude, invisible to smaller instruments, lost in the noise of the night sky. The search team has photographed the region of sky ahead of New Horizons' trajectory, looking for faint points of light that move against the background stars, their motion revealing them as solar system objects rather than distant galaxies. Hundreds of hours of telescope time have been devoted to this search, thousands of images analysed, millions of stellar sources examined for telltale motion. The results have been frustrating. Several candidate objects have been identified, faint points that appear to move at roughly the expected rate for distant Kuiper Belt objects. But determining whether any of these candidates lie close enough to New Horizons' path to permit a flyby requires additional observations, careful tracking of their orbits over months or years to calculate future positions with the precision needed for spacecraft targeting. Some candidates have proven to be false positives, their apparent motion revealed as errors in the data processing. Others have turned out to be real objects but unreachable, their orbits passing too far from the spacecraft's trajectory to allow close approach. The search continues, hope persisting despite repeated disappointment. A single discovery could transform the extended mission, providing a target for the spacecraft's final years, a third ancient body to examine before the power runs out. The object would not be chosen for its scientific interest but for its accessibility, its fortunate position near a trajectory that was never designed to encounter it. Whatever properties such an object possessed would be studied not because they were particularly compelling, but because the object was there, and the spacecraft was there, and the universe briefly aligned to permit an encounter. This is exploration at its most opportunistic. Science conducted not according to plan, but according to circumstance. The team has named this potential third target the KBO3 opportunity, a designation that acknowledges both its tentative nature and its potential significance. Modelling suggests that if a suitable object is found, the flyby would occur sometime in the early 2030s, when New Horizons will be more than 70 astronomical units from the Sun, nearly twice Pluto's distance. The spacecraft will be older then, its power diminished, its instruments perhaps partially disabled by accumulated radiation damage or component failures. But if the RTG still produces enough electricity to operate the cameras and transmitter, if the spacecraft's health permits, another encounter remains possible. The team refuses to abandon the search while any chance remains. Meanwhile, the spacecraft continues its particle and plasma measurements, building a record of conditions in the outer heliosphere that grows more valuable with each passing day. The solar wind at these distances has never been sampled before in this sector. The Voyagers crossed through different regions of the heliosphere, exiting near the nose of the bubble where the Sun's motion through interstellar space compresses and shapes the boundary. New Horizons is travelling more toward the flank where the bubble's edge may be farther from the Sun and differently configured. The measurements will help scientists understand the heliosphere's three-dimensional structure, the way the Sun's influence extends outward in some directions and is constrained in others. The dust measurements continue as well. The student dust counter operates independently of the main spacecraft systems, requiring minimal power and generating small amounts of data that can be transmitted during routine communication sessions. The counter has now detected impacts from Kuiper Belt dust across more than 40 astronomical units of travel, a baseline unprecedented in the history of planetary science. The data reveal a dust disk that extends far beyond the classical Kuiper Belt, particles spread throughout the outer solar system by billions of years of collisions and orbital evolution. This disk is the solar system's equivalent of the debris disks seen around other stars, the faint rings of material that planet formation theories predict and telescopes increasingly observe. New Horizons is driving through our own debris disk, measuring it from the inside in ways that distant observation could never replicate. The student dust counter also represents something beyond pure science. The instrument was built by undergraduate students at the University of Colorado, designed and constructed as an educational project that happened to produce flight-worthy hardware. The students who built the counter graduated years ago, their careers having carried them to positions throughout industry and academia. But their instrument still operates, still records impacts, still contributes to the mission's scientific return. The counter is a testament to what students can achieve when given meaningful work, when trusted with responsibilities typically reserved for experienced professionals. It is also a reminder that space missions are not just spacecraft, but people, communities of effort that extend across institutions and generations. The energetic particle measurements have revealed something unexpected about the outer solar system. The intensity of galactic cosmic rays, the high-energy particles that originate outside our solar system and rain down through interstellar space was expected to increase as New Horizons travelled outward, and the shielding effect of the solar wind diminished. This general trend has been confirmed. Cosmic ray intensity is indeed higher at 58 astronomical units than it was at Pluto's distance, and higher still than it was during the cruise through the inner solar system. But the increase has not been smooth or monotonic. There are structures in the cosmic ray data, variations that suggest the heliosphere's shielding effect is not uniform, that there are regions of greater and lesser protection scattered through the Sun's domain. These structures may be related to the solar wind itself, to irregularities and disturbances that propagate outward from the Sun and create temporary zones of enhanced or reduced shielding, or they may reveal something about the interaction between the heliosphere and the local interstellar medium, about the way the bubble's edge flexes and deforms in response to conditions beyond the Sun's influence. The Voyagers detected similar structures as they approached the heliopause, but they passed through the nose region, where conditions differ from the flank where New Horizons travels. Comparing measurements across the spacecraft, triangulating conditions in three-dimensional space, scientists are beginning to map the heliosphere's interior with detail that decades of theoretical modelling could not achieve. The spacecraft carries a time capsule of sorts, though not the deliberate kind that Voyager famously bears. Where the Voyagers carry golden records encoded with images and sounds of Earth, messages intended for hypothetical alien discoverers in the distant future, New Horizons carries only the artifacts of its mission. A small piece of Pluto's discoverer's ashes, mounted inside the spacecraft before launch, an American flag, folded and stowed among the electronics, a Maryland state quarter, recognition of where the spacecraft was built, a Florida state quarter, acknowledgement of where it launched, a 1991 US postage stamp declaring Pluto, not yet explored, now definitively outdated. A compact disc containing the names of 434,538 people who signed up to send their names to Pluto, a digital monument to public enthusiasm for exploration. These artifacts will outlast the mission's scientific return by billions of years. When the power fails and the transmissions cease, when the spacecraft becomes a drifting hulk tumbling slowly through the darkness, these objects will remain. The plutonium will eventually decay to stable lead. The electronic components will fail from cosmic ray damage and thermal cycling and simple material fatigue. The solar system will continue its slow evolution, stars dying and being born, the Milky Way continuing its stately rotation around a supermassive black hole. And somewhere in that galaxy, a small spacecraft built by small creatures on a small planet will drift onward, carrying its cargo of human meaning through spaces that care nothing for meaning, a message that no one may ever receive. But that silence lies years in the future. Today, the spacecraft still functions, the instruments still measure, the transmitter still sends. The mission continues because it can continue, because people on Earth still want to know what lies beyond, because the data still flows and the questions still demand answers. Every measurement extends the baseline. Every observation adds to the catalogue. Every day the spacecraft survives is a day that expands human knowledge of the outer solar system. The relationship between New Horizons and Earth has evolved over the mission's lifetime. In the early years during cruise to Pluto, the spacecraft was one project among many, monitored and maintained but not central to planetary science discourse. During the Pluto encounter, it became the focus of global attention, its images appearing on front pages and magazine covers, its discoveries discussed in classrooms and living rooms around the world. That intense attention faded after the flyby, media focus shifting to newer missions, fresher discoveries, more immediate stories. The Arrokoth encounter generated another peak of interest, smaller than Pluto but still significant, and then attention faded again. Now New Horizons operates in a kind of dignified obscurity. The mission continues, the science proceeds, but few people outside the planetary science community pay attention. The spacecraft has become infrastructure, a permanent feature of the outer solar system exploration landscape, taken for granted in ways that belie the extraordinary engineering and devotion that keep it functioning. The team members who operate New Horizons are accustomed to this obscurity. They measure success not in headlines but in data return, in instrument health, in the steady accumulation of knowledge that may not generate excitement but generates understanding. This quiet work has value that transcends individual discoveries. The extended mission demonstrates something important about what humanity can accomplish when resources are committed over timescales that exceed individual careers and political cycles. New Horizons launched in 2006, reached Pluto in 2015, encountered Arrokoth in 2019, and will continue operating into the 2030s. The mission spans 3 decades, at minimum. Some scientists who will analyse the final data from the extended mission were not yet born when the spacecraft launched. The mission connects generations, transmitting knowledge from past to future, demonstrating that exploration is not a sprint but an ultramarathon. The spacecraft itself is a bridge across time. It was designed using early 2000s technology, built with components that would be considered primitive by current standards, programmed with software that predates the smartphone era. Yet, it still works. The design was robust enough to survive 2 decades of operation, the engineering sound enough to continue functioning far beyond planned lifetime. This durability was not accidental. It was purchased through careful analysis, conservative design margins, exhaustive testing, and the accumulated wisdom of previous missions that failed in ways New Horizons was built to avoid. The spacecraft is a repository of engineering knowledge, a testament to what happens when smart people are given adequate resources and held to high standards. The transmissions from New Horizons travel for 8 hours to reach Earth, spreading as they travel, the signal weakening with the square of the distance. By the time those transmissions arrive, they are incomprehensibly faint, whispers against the background noise of the universe. The Deep Space Network's antennas must strain to hear them, integrating weak signals over long periods to extract the meaningful patterns from the random fluctuations. This straining will intensify as the spacecraft recedes, as the distance grows and the power drops, and the signal weakens further still. Eventually the straining will fail. Eventually the whispers will fade below detectability. Eventually the spacecraft will be broadcasting to no one, its transmitter still attempting to reach home, but its signals too weak to be received. That day has not yet arrived. The antennas still hear, the data still flows, the spacecraft still reports its findings from the edge of the solar system, from regions no probe has visited before, from darkness that human senses could never pierce. And every day it continues, the mission accomplishes something its builders never fully anticipated. It demonstrates that exploration does not end when the primary mission concludes, that spacecraft can keep discovering long after the champagne has been drunk and the press releases have been written, that the universe always has more to reveal to those patient enough to keep looking. The patient observers who continue looking have expanded their search in ways the original mission planners never anticipated. The Kuiper Belt is not merely a region to be traversed, a zone to be passed through on the way to somewhere else. It is a destination in itself, a vast reservoir of frozen history that preserves information about the solar system's earliest days in ways that no inner solar system object can match. New Horizons has transformed from a flyby mission to an exploration platform, from a camera passing through to a laboratory embedded within its subject of study. The instruments aboard the spacecraft were designed with specific targets in mind. Alice was built to study Pluto's atmosphere. Ralph was optimized for Pluto's surface. Rex was tuned for radio experiments with Pluto and its moons. But instruments, like missions, can exceed their original purposes. The same detectors that mapped Pluto's nitrogen glaciers can detect ultraviolet emissions from interplanetary hydrogen. The same cameras that revealed Arakoth's contact binary structure can measure how light scatters off dust particles too small to see individually. The same radio equipment that probed Pluto's atmospheric layers can track how the solar wind changes as it pushes outward into the void. Each instrument has found secondary applications, tertiary uses, purposes that were theoretical possibilities during design, but have become practical realities during operation. The dust counter deserves particular attention because it embodies what the extended mission has become. The Venetia Burney student dust counter was included partly as an educational project, a way to involve students in real space science, a modest instrument with modest expectations. It measures the impact of dust particles on a thin film, registering each collision as a tiny electrical signal, counting the grains of matter that pervade the seemingly empty spaces between worlds. During the cruise to Pluto, the dust counter provided a census of the inner solar system's particulate environment, data that was useful but not revolutionary. After Pluto, the instrument entered unexplored territory. No spacecraft had ever measured dust densities in the outer Kuiper Belt. The student instrument became a primary science tool. What the dust counter found challenged existing models. The concentration of dust did not decline smoothly with distance from the Sun, as simple models predicted. Instead, the data revealed structure, variations in density that suggested ongoing processes rather than static distribution. Collisions between Kuiper Belt objects create fresh dust constantly. That dust slowly spirals inward under the influence of solar radiation pressure, joining the general circulation of particles that fills the solar system. But the rates of dust production, the sizes of particles created, the efficiency of their removal mechanisms, all of these parameters were poorly constrained before New Horizons provided direct measurements. The student dust counter is rewriting the textbooks on outer solar system particle environments, one microscopic impact at a time. The plasma instruments tell an equally compelling story. The solar wind around Pluto experiment, known as SWAP, and the Pluto Energetic Particle Spectrometer Science Investigation, known as PEPSI, were designed to characterize how the solar wind interacts with Pluto's thin atmosphere. They accomplished that primary goal during the flyby, detecting how Pluto's escaping nitrogen creates a bow shock in the solar wind, how energetic particles are accelerated at the interface between planetary atmosphere and interplanetary medium. But after the flyby, these same instruments pivoted to a different question. What happens to the solar wind as it travels ever outward, ever farther from its source? The solar wind is the sun's continuous exhalation, a stream of charged particles flowing outward at hundreds of kilometers per second, carrying the sun's magnetic field into interplanetary space. This wind does not blow forever. At some distance, it encounters the interstellar medium, the tenuous gas and dust that fills the space between stars. The collision between solar wind and interstellar medium creates a boundary zone, a region of compressed and heated plasma where the Sun's influence gives way to the galaxy's. Voyager 1 crossed this boundary in 2012. Voyager 2 crossed it in 2018. Both spacecraft detected the transition. Both measured the change conditions on the far side. But both Voyagers crossed in roughly the same direction, leaving much of the boundary unexplored. New Horizons will provide a third crossing, but from a different angle. The spacecraft's trajectory takes it through a different sector of the heliosphere's edge, probing regions neither Voyager visited. The solar wind varies with solar latitude and longitude. The interstellar medium is not uniform. The boundary between them may have different characteristics in different directions. New Horizons will test this, will determine whether the heliospheric boundary is symmetric or asymmetric, whether the transition is equally sharp in all directions or varies with local conditions. This measurement was not part of the original mission plan. Pluto lies well inside the heliosphere. The flyby was never intended to study the solar system's outermost boundary, but the spacecraft's continued health and the team's ingenuity have opened this possibility, have transformed a Pluto mission into a heliospheric probe. The timeline for this transformation stretches across decades. New Horizons will likely reach the termination shock, the innermost boundary where the solar wind first begins slowing, sometime in the late 2020s or early 2030s. It will reach the heliopause, where the solar wind stops entirely, perhaps a decade later, assuming the spacecraft survives that long. These are estimates, approximations based on current models of heliospheric structure. The actual boundaries may be closer or farther, the crossing times earlier or later. Uncertainty pervades these predictions because the heliosphere breathes with the Sun's activity cycle, expanding when the Sun is active and contracting when it's quiet. The boundary that Voyager 1 crossed may have moved since then, may move again before New Horizons arrives. The scientific instruments are aging along with the spacecraft that carries them. 20 years in the harsh radiation environment of space takes a toll on sensitive electronics. Detectors degrade, amplifiers drift, calibrations shift. The team monitors these changes carefully, tracking each instrument's performance over time, adjusting analysis techniques to compensate for known degradation patterns. Some instruments have lost sensitivity, others have developed quirks that must be worked around. The spacecraft is not what it was when it launched, cannot be what it was, entropy being the universal tax on all organized systems. But it remains functional. It remains capable of science. The degradation has been slow enough, manageable enough, that the mission continues to produce valuable data despite the accumulated wear of 2 decades. Power constraints increasingly shape mission operations. The radioisotope thermoelectric generator that provides electricity to New Horizons produces less power each year as its plutonium-238 fuel decays. At launch, the generator produced about 245 watts. By the time of the Pluto flyby, that had declined to approximately 202 watts. Today, it produces roughly 190 watts, and by the early 2030s it will produce perhaps 170 watts. These numbers might seem modest, less than a bright incandescent bulb, but they represent all the energy available for everything the spacecraft does: heating critical components, running computers, powering instruments, transmitting data home. Every watt matters. Every system competes for limited power. The mission planners have developed increasingly sophisticated power management strategies to cope with declining resources. Instruments that once operated continuously now operate in campaigns, turned on for specific observations, and then switched off to conserve power for other systems. Heating that once maintained comfortable temperatures now maintains merely survivable ones. Data transmission rates have been reduced to allow the transmitter to operate at lower power levels. These adaptations have preserved the mission's scientific productivity even as its energy budget shrinks. The team has become expert at doing more with less, at extracting maximum science from minimum resources, at finding creative solutions to problems that grow more constraining each year. The thermal challenges are particularly acute. Space is cold, but not uniformly cold. Objects in sunlight absorb solar radiation and warm. Objects in shadow radiate heat into the void and cool. Spacecraft are patchworks of different materials with different thermal properties, some areas receiving sunlight, others in permanent shadow, heat flowing from warm regions to cold through conduction and radiation. Maintaining acceptable temperatures across this thermal patchwork requires careful design and active management. Heaters keep critical components above their minimum operating temperatures. Thermal blankets reduce heat loss from sensitive areas. Louvers and radiators allow controlled heat rejection when cooling is needed. All of these systems require power that is becoming scarcer. The spacecraft's thermal engineers face an ongoing challenge. As power declines, less energy is available for heating, but the heating requirements do not diminish. Some components have minimum temperature ratings below which they cannot safely operate. If temperatures drop too low, materials become brittle, electronics malfunction, fuel lines freeze. The engineers must prioritize which components receive heating and which are allowed to cool, must make difficult choices about acceptable risks, must balance the desire to preserve all systems against the reality that not all systems can be preserved indefinitely. Some instruments may eventually be abandoned, allowed to cool below operating temperatures and effectively turned off permanently, their power reallocated to systems deemed more essential for continuing operations. The attitude control system presents its own long-term concerns. New Horizons maintains its orientation in space using a combination of star trackers, sun sensors, and inertial measurement units. These sensors tell the spacecraft where it is pointing. Small thrusters fire brief pulses to adjust that pointing, to keep the antenna aimed at Earth, to orient the instruments toward observation targets, to maintain the precise alignment required for communication and science. The thrusters consume hydrazine propellant, a finite resource that cannot be replenished. The mission launched with approximately 77 kilograms of hydrazine. Each maneuver consumes a small amount. The Pluto and Arrokoth flybys required significant propellant expenditure for course corrections and targeting. What remains must last for the duration of the extended mission. Propellant usage has been carefully tracked and minimized. The team has developed techniques to reduce the frequency of attitude adjustments, to combine maneuvers that once would have been separate, to operate in modes that require less active control. These conservations have extended the propellant lifetime, have pushed the mission's viable operational period further into the future. Current projections suggest propellant will not be the limiting factor, that power will likely constrain operations before propellant runs out. But projections are not guarantees. Unexpected events could change the calculation. A failed thruster could require compensating firings from others. A targeting opportunity for a Kuiper Belt object could require propellant that had been reserved for maintenance. The margin is comfortable, but not infinite. The communication link presents perhaps the most fundamental constraint on the extended mission. New Horizons transmits data using X-band radio frequencies, the same frequencies used by many interplanetary spacecraft, chosen for their favorable propagation characteristics and the availability of ground-receiving equipment. The spacecraft's high-gain antenna is 2.1 meters in diameter, modest by deep space standards but adequate for the data rates required by the mission. At Pluto distance, this antenna could transmit at approximately 1,000 bits per second during the most favorable conditions. From Arrokoth, the rate dropped to roughly 500 bits per second. From the spacecraft's current position, rates have declined further still. These data rates would seem painfully slow to anyone accustomed to modern internet connections. A single high-resolution image from New Horizons might contain tens of megabytes of data. At 500 bits per second, transmitting such an image would require days. The spacecraft must carefully select which data to prioritize, compressing observations where possible, downlinking the most important results first, sometimes discarding less critical measurements to make room for more valuable ones. Data management has become an exercise in triage, in determining what matters most, in accepting that not everything collected can be returned to Earth. The deep space network that receives these transmissions is a shared resource. 3 complexes around the world, in California, Spain and Australia, provide the giant antennas needed to communicate with humanity's most distant spacecraft. New Horizons is not the only mission requiring these antennas. Mars orbiters, Jupiter probes, solar observatories, and other deep space missions all compete for limited antenna time. Scheduling is a constant negotiation, a balancing of priorities, a recognition that resources serving all of humanity's space exploration efforts cannot be monopolized by any single mission. New Horizons has learned to make the most of its allocated antenna time. Data is queued in priority order, with the most important measurements transmitted first in case contact is interrupted. Transmission protocols have been optimized to maximize throughput during favorable conditions. Duplicate transmissions provide error correction without requiring retransmission requests that would waste precious contact time. These efficiencies have allowed the mission to return far more data than raw bit rates would suggest, have demonstrated that clever engineering can partially compensate for fundamental physical limitations. The team has also explored whether additional ground stations could extend the mission's reach. The giant radio telescopes used for astronomy can sometimes be borrowed for spacecraft communication, their vast collecting areas amplifying signals that would be too faint for dedicated deep space antennas. The Greenbank Telescope in West Virginia, with its 100-meter dish, could potentially receive New Horizons data at rates significantly higher than the Deep Space Network alone allows. These arrangements require coordination between different scientific communities, between agencies and institutions with different priorities and schedules. Such coordination takes effort, but has sometimes been achieved, creating opportunities for enhanced data return during critical mission phases. The data that flows back through these tenuous connections feeds a community of scientists who have dedicated their careers to understanding the outer solar system. Some of these scientists have worked on New Horizons since its conception in the early 2000s. Others joined more recently, attracted by the Pluto results or the Arakoth discoveries, drawn to the opportunity to study objects that had been mere points of light throughout their graduate training. The scientific community that New Horizons supports is multi-generational, connecting researchers at every career stage, providing data that feeds dissertations and landmark papers alike. The interpretation of New Horizons data requires collaboration with theorists, modelers, and laboratory scientists who have never touched spacecraft hardware. The Arakoth images inspire computer simulations of accretion processes, attempts to understand how two separate bodies could merge so gently. The Pluto atmospheric measurements feed into climate models that track how nitrogen cycles between surface ice and tenuous atmosphere. The dust counter data constrains models of collision rates among Kuiper Belt objects, helping calibrate estimates of how frequently these distant bodies crash into each other. The spacecraft is a data source, but the science requires a broad community to interpret what that data means. Some interpretations remain contentious. Scientists disagree about the implications of certain measurements, about which models best explain observed phenomena, about priorities for future observations. This disagreement is healthy, is how science progresses, is the mechanism by which wrong ideas are identified and discarded. New Horizons has generated debates that will take years to resolve, has raised questions that may not be answered until future missions provide additional data. The spacecraft's role is not to end debates, but to inform them, to replace speculation with measurement, to narrow the range of possibilities that theorists must consider. The search for additional flyby targets has shifted from necessity to opportunity. After Arakoth, the team confirmed that no other reachable object of comparable size exists along the spacecraft's trajectory. The search techniques that found Arakoth have been applied again and again, but the outer Kuiper Belt is simply too sparse, its objects too faint, the spacecraft's fuel too limited for the large course corrections that might reach something comparable. Any future close encounter will be with something small, something that would have been invisible to the ground-based surveys, something that might be detected only at the last moment through the spacecraft's own cameras. The possibility of such a discovery adds a lottery-like element to the extended mission. The team continues observing ahead of the spacecraft, scanning for anything that might emerge from the blackness, any flicker of reflected light that might betray an object's presence. The odds are long, the volumes of space are vast, the probability of encountering anything larger than a dust grain without deliberate targeting is exceedingly small. But exceedingly small is not zero. The spacecraft might stumble across something unexpected, might provide bonus science that no one planned for, might once again demonstrate that exploration rewards those who persist beyond the obvious accomplishments. Even without a close flyby, remote sensing continues providing valuable data. The cameras can observe Kuiper Belt objects at distances of hundreds of millions of kilometers, measuring their brightness as they rotate, detecting variations that reveal shape, composition, perhaps even surface features if the objects are large enough and bright enough. These distant observations lack the detail of close flybys, but provide information unavailable from Earth. The spacecraft's vantage point outside the inner solar system offers viewing geometries that ground-based telescopes cannot achieve. Light scattering behaves differently at different angles. Objects that appear one way from Earth might appear quite differently from New Horizons' perspective. The team has developed techniques for extracting maximum information from these distant observations. Phase angle measurements reveal surface roughness and texture. Color ratios suggest compositional variations between objects. Light curve analysis constrains rotation periods and shapes. None of this replaces the wealth of data a close flyby would provide, but it expands knowledge of the Kuiper Belt population in ways that ground-based surveys cannot. Every observation adds another data point to the emerging picture of what the outer solar system contains. The spacecraft's position outside the zodiacal dust cloud that pervades the inner solar system offers another scientific opportunity. Zodiacal light, the faint glow that can be seen after sunset or before sunrise under dark skies, comes from sunlight scattered by dust particles concentrated near the plane of the solar system. This dust fills the inner solar system with a haze that complicates astronomical observations. From New Horizons' distant vantage, the zodiacal dust is behind the spacecraft, its contribution to the sky background greatly reduced. The cosmic background that remains is cleaner, less contaminated by local effects, better suited for measuring faint and diffuse phenomena. The team has used this advantage to measure the cosmic optical background, the accumulated light from all the galaxies in the universe, minus those that telescopes can individually resolve. This measurement addresses a fundamental question in cosmology. Is there light in the universe that cannot be accounted for by known sources? Careful analysis of New Horizons images, after subtracting all identified sources of light, suggests that the answer may be yes. The cosmic optical background appears slightly brighter than models predict, implying either that galaxies are more luminous than thought, that there are more faint galaxies than surveys have counted, or that some unknown source contributes to the universal glow. This measurement was not part of the original mission plan. It emerged from creative use of existing instruments for purposes their designers never anticipated. The spacecraft that was built to photograph Pluto has become, in its quiet way, a cosmological observatory. The same cameras that captured the haze layers of Pluto's atmosphere and the nitrogen glaciers of Sputnik Planitia now peer into the depths of intergalactic space, measuring the accumulated glow of billions of years of stellar evolution. The same detectors that mapped the frozen nitrogen and methane ices of Arakoth's surface now contribute to debates about the total energy output of the cosmos. This transformation was not planned. It was discovered, improvised, pulled from the capabilities of instruments that turned out to be more versatile than their designers realized. The cosmic optical background measurement exemplifies a broader truth about exploration. Missions often return their greatest dividends in areas no one anticipated. The scientists who designed New Horizons cameras were thinking about surface features, albedo variations, spectral signatures of icy compounds. They were not thinking about measuring the total light output of the universe, but the instruments they built, because they were built well, because they were designed with sufficient precision and stability, turned out to be useful for purposes that lay entirely outside the original mission concept. The spacecraft's journey beyond the zodiacal dust cloud created an opportunity that exists nowhere else in the solar system, an opportunity that would have been wasted if the team had not been creative enough to recognize it and skilled enough to exploit it. The measurement itself required extraordinary care. The cosmic optical background is faint beyond ordinary comprehension. It represents the total light reaching any point in space from all external sources, integrated over the entire history of the universe. Stars have been forming and dying for over 13 billion years. Galaxies have been assembling, colliding, merging, creating new stars and consuming old ones. All of that activity produces light. Most of that light comes from sources too distant or too faint to be individually detected, but it does not disappear. It accumulates, filling the universe with a diffuse glow that pervades all of space. Measuring this glow requires separating it from every other source of light in the sky, a task of almost impossible delicacy. The team had to account for scattered light within the spacecraft itself, reflections from the antenna and other structures that might contaminate the images. They had to subtract the contribution of known stars, galaxies, and other sources that could be individually identified. They had to model the residual zodiacal light that still reaches the spacecraft's position, attenuated but not entirely eliminated. They had to understand the behavior of their detectors with a precision that would have seemed excessive for any purpose contemplated during mission design. Every source of systematic error had to be identified, characterized, and removed. What remained, after all subtractions, was a measurement of surprising implications. The cosmic optical background appeared brighter than standard models predicted. The excess was small but statistically significant, representing perhaps twice as much light as could be accounted for by summing up the contributions of known galaxy populations. This discrepancy, if confirmed, demands explanation. Either galaxies are more luminous than surveys suggest, perhaps because faint outer regions contribute more light than previously thought, or there are more galaxies than counts have detected, perhaps because extremely faint dwarf galaxies pervade the universe in numbers that surveys have missed. Or there is some additional source of light that current models do not include, some phenomenon that contributes to the cosmic glow without leaving other obvious signatures. The New Horizons measurement does not resolve this question. It opens it. The data suggest that something about our understanding of the universe's light output is incomplete, but they do not specify what that something is. Other measurements, other techniques, other instruments will be needed to determine whether the excess is real, and if so, what causes it. But the measurement itself could not have been made from anywhere in the inner solar system. The zodiacal dust that pervades the space around Earth creates too much contamination, too much scattered light that cannot be fully characterized or removed. Only by travelling billions of miles beyond that dusty region could the measurement become possible. New Horizons has carried its instruments to a location that offers unique scientific opportunities, and the team has proved ingenious in recognizing and exploiting those opportunities. The spacecraft is not simply travelling through the outer solar system. It is operating an observatory in a location no human-made instrument has ever occupied, using that location to conduct observations that would be impossible from anywhere closer to the Sun. This observatory continues operating, continues returning data, continues contributing to fields far removed from planetary science. But its capabilities are slowly, inexorably diminishing. The plutonium that powers everything, the alpha particles whose heat is converted to electricity, follows its own immutable schedule. Plutonium-238 has a half-life of 87.7 years. Every 87.7 years, half of the remaining plutonium atoms undergo decay, releasing their energy and transforming into uranium-234. This decay cannot be accelerated or decelerated. It cannot be paused or extended. It proceeds at exactly the rate that nuclear physics dictates, regardless of human needs or scientific opportunities. When New Horizons launched in January 2006, its radioisotope thermoelectric generator contained approximately 11 kilograms of plutonium dioxide, incorporating about 4.8 kilograms of plutonium-238. This plutonium produced roughly 245 watts of thermal power, which the generator converted into about 240 watts of electrical power. The conversion efficiency is not high. Most of the heat radiates away into space, wasted. Only a small fraction becomes the electricity that powers instruments, heaters, computers, and transmitters. But that small fraction was enough. It was enough to operate all systems during cruise, during encounters, during the long years of heliophysics measurements and Kuiper Belt observations. By the time of the Pluto flyby in July 2015, the plutonium had been decaying for over 9 years. The thermal output had dropped to approximately 202 watts. The electrical power available had fallen to roughly 190 watts. The spacecraft could still operate all instruments, could still warm all heaters, could still transmit at full power. But the margins had narrowed. Every watt mattered more than it had at launch. By the Arakoth flyby in January 2019, another 3.5 years of decay had occurred. The thermal output had dropped to approximately 190 watts. The electrical power had fallen to roughly 175 watts. The team had learned to manage with less, had developed procedures for conserving power when possible, had prioritized the most essential functions during the most critical operations. But the trajectory was clear. The power would continue falling. The options for managing that decline would continue narrowing. Now, as the spacecraft pushes deeper into the Kuiper Belt, approaching 50 astronomical units from the Sun, the plutonium output has dropped further still. Current estimates place the thermal output around 170 watts, the electrical output around 155 watts. These numbers will continue declining for as long as the spacecraft exists, dropping by roughly 4 watts per year, a slow and steady diminishment that cannot be reversed. The implications of this decline ripple through every aspect of mission operations. Instruments that once operated continuously must now be time-shared, turned on for specific observations and turned off when not needed. Heaters that once kept all components within their preferred temperature ranges must now be rationed, with some systems allowed to drop to temperatures that would have been considered unacceptable during the primary mission. The spacecraft must make choices that were never contemplated during design, must accept compromises that would have seemed like failures when the mission launched. The team has developed elaborate power management strategies to maximize science return within these constraints. They have identified which instruments provide the most valuable data and prioritize power allocation accordingly. They have determined which heaters are truly essential and which can be reduced or eliminated. They have learned to operate the spacecraft in modes that would have been considered risky during the primary mission, accepting increased probability of problems in exchange for extended operational lifetime. The most critical constraint is the deep space network communication link. Transmitting data across billions of miles requires power. The spacecraft's transmitter operates at roughly 12 watts, not a large number compared to radio stations on Earth, but a significant fraction of the dwindling power budget. More importantly, the rest of the spacecraft must continue operating while transmissions occur. Computers must process commands and format data. Recorders must read stored information. Attitude control systems must keep the antenna pointed at Earth with millimeter precision. All of these systems draw power. All of these systems must function simultaneously during communication passes. As power declines, the team has had to become increasingly creative about scheduling observations and communications. They cannot simply turn everything on and let it run. They must carefully plan when each instrument operates, when data is recorded, when transmissions occur. They must balance the desire for maximum science return against the need to preserve power for essential functions. They must accept that some observations will never be possible because the power simply is not available. The thermal management challenge grows more severe with each passing year. Space is cold, colder than any environment on Earth, colder than anything in ordinary human experience. The temperature of deep space, far from any star, approaches absolute zero, just a few degrees above the point where all thermal motion ceases. Electronic components designed for operation in that environment must be kept warm enough to function. Lubricants in mechanical systems must remain above their freezing points. Batteries must stay within their operating temperature ranges. All of this requires heat, and all of that heat ultimately comes from the plutonium. As the plutonium output declines, the spacecraft cannot maintain all components at their original temperatures. The team has had to identify which systems can tolerate colder conditions and which cannot. They have reduced heater set points where possible, allowing temperatures to drift downward toward the minimum specifications. They have accepted that some components will operate at the cold end of their design ranges, where performance may be slightly degraded, but failure is not expected. They have studied the behavior of similar components in laboratory tests, trying to understand exactly how cold is too cold, exactly where the margin between acceptable operation and failure lies. Some systems have already been powered down, their functions deemed expendable in the quest to preserve the spacecraft's core capabilities. Others operate only intermittently, activated for specific observations and then returned to cold storage. The spacecraft that once operated with comfortable margins now runs lean, every watt accounted for, every thermal joule precious. The student dust counter continues operating through all of these constraints. Its power requirements are modest, just a few watts when active, and the measurements it provides are unique. No other instrument anywhere in the solar system can measure the dust environment at the distances New Horizons has reached. The data it returns constrains models of debris production in the Kuiper Belt, models that have implications for understanding how planetary systems form and evolve. The team has prioritized keeping this instrument functional for as long as power permits. The plasma instruments continue operating as well, though with reduced duty cycles. The solar wind measurements at extreme heliocentric distances contribute to understanding of how the Sun's influence propagates through interplanetary space. The data reveal variations in solar wind density and velocity that reflect conditions millions of miles sunward, information that helps model the complex dynamics of the heliosphere. These measurements complement those from Voyager 1 and Voyager 2, which are now operating in interstellar space, beyond the boundary where solar wind gives way to the interstellar medium. New Horizons fills the gap between the inner solar system and the heliopause, providing measurements from a region that would otherwise be entirely unsampled. The cameras remain functional, though their use must be carefully rationed. Each imaging session requires power for the camera itself, power for the digital electronics that process the images, power for the solid-state recorders that store the data. The team must decide which observations justify these expenditures, which targets merit the investment of precious watts. Distant Kuiper Belt objects receive attention when geometries are favourable. The cosmic optical background measurements continue when conditions permit. Occasional calibration images verify that the instruments remain healthy, but the cameras no longer operate freely. Every use represents a choice, a decision that some other observation will not occur. The Ralph instrument, the sophisticated imaging spectrometer that produced the most detailed maps of Pluto and Arrokoth, requires more power than the simpler cameras. Its use has become increasingly rare, reserved for high-value targets that justify the expenditure. The same is true for other power-hungry systems. The spacecraft must now be selective in ways it never was before, must prioritize ruthlessly among scientific opportunities that once would all have been pursued. The team has estimated that meaningful science operations can continue until roughly 2030, perhaps a few years beyond if power management techniques prove more effective than expected. After that point, the electrical output will have dropped below the level needed to operate instruments, communicate with Earth, and maintain essential systems simultaneously. Some functions might persist beyond that date in degraded form, but the spacecraft's scientific productivity will effectively end. The question of what happens after that remains open. The spacecraft will continue travelling outward regardless of its operational status, carried by the momentum imparted during that Jupiter gravity assist in February 2007. By the late 2030s, New Horizons will have passed 55 astronomical units from the Sun, deeper into the Kuiper Belt than any previous spacecraft. By the 2040s, it will approach 60 astronomical units, regions that current surveys have barely begun to characterize. By mid-century, it will be moving through territories that exist, for all practical purposes, as blank spaces on our maps. But the spacecraft will be silent by then. Its plutonium will have decayed below the threshold for useful power generation. Its instruments will be cold, their electronic circuits inert. Its transmitter will be dead, unable to send even the weakest signal back to Earth. The spacecraft will continue existing as a physical object, a collection of metal and plastic and silicon traversing the outer darkness, but it will no longer be an extension of human perception. It will be a monument rather than an instrument. The trajectory that carries New Horizons outward leads, eventually, toward the stars. Not toward any particular star, not toward any destination that might be reached in any time frame meaningful to human planning, but outward nonetheless, away from the Sun's gravitational dominance, toward the regions where the Sun becomes just another point of light among millions. The spacecraft will leave the solar system entirely, crossing the heliopause as the Voyagers have done, entering the interstellar medium that fills the galaxy between stars. This crossing will occur around 2040 or shortly thereafter, roughly a decade after the spacecraft falls silent. By then, the Voyagers will have been in interstellar space for over 2 decades. They will have mapped the local interstellar environment, measured the density and temperature and magnetic field of the material between stars, provided humanity's first direct sampling of the medium through which the Sun and all its planets move. New Horizons will enter that same medium travelling in a different direction, offering the possibility of sampling interstellar conditions along a different path. But the spacecraft will not be able to report what it finds. Its instruments will be silent. Its journey through interstellar space will go unwitnessed. This prospect gives the remaining years of the mission a particular poignancy. Every measurement New Horizons makes now, every observation it returns, represents data that will never be replicated. No other spacecraft is travelling through the outer Kuiper Belt. No other mission is currently planned to follow this path. The observations that New Horizons collects before its power runs out constitute a singular scientific legacy, information about regions of the solar system that may not be visited again for decades, perhaps longer. The team understands this. They approach the extended mission with an urgency that belies the spacecraft's leisurely pace. Every day of operation is precious. Every downlink session retrieves data that expands human knowledge of the distant solar system. Every power management decision represents a bet about which observations will matter most when historians eventually assess what the mission accomplished. The choices are not always obvious. Some observations that seem routine might prove more valuable than expected. Some high-priority targets might yield less insight than hoped. The team must decide without knowing the answers, must allocate resources based on their best judgment about where the greatest discoveries lie. They have chosen to emphasize several scientific themes during the extended mission. The heliophysics measurements continue, building the long-duration data set that reveals how solar wind evolves with distance from the Sun. The dust measurements continue, mapping the debris environment through regions never before sampled. The cosmic optical background observations continue when geometries permit, contributing to cosmological questions far removed from the original mission objectives. And the search for additional Kuiper Belt objects continues, the faint hope that something might emerge from the darkness, that one more close encounter might somehow be possible before the power runs out. This last hope has driven a sustained observation campaign using the spacecraft's cameras. The team scans the region ahead of the spacecraft, looking for any point of light that might move against the background stars, any flicker that might betray an object's presence. The searches are painstaking and largely fruitless. The objects out here are small and dark, reflecting only tiny fractions of the feeble sunlight that reaches them. Most are far too faint to detect even with New Horizons cameras at their maximum sensitivity. The spacecraft would need to pass quite close to such an object to image it, and the probability of such a passage occurring by chance is vanishingly small. But vanishingly small is not zero. The universe has surprised observers before. The Kuiper Belt has already demonstrated that it contains more variety than early models predicted. The possibility that New Horizons might encounter something unexpected, something that would provide one final burst of discovery data before the power fails, keeps the search worthwhile. The lottery ticket costs little to hold. The potential payoff, while unlikely, would be extraordinary. The observation sequences that support this search also produce valuable science, even when they find nothing. The images of star fields taken from New Horizons' distant vantage point enable precise astrometric measurements. Stars that appear in slightly different positions from the spacecraft's perspective than from Earth's perspective reveal their distances through the parallax effect. Some of these parallax measurements are more precise than those available from ground-based observatories, contributing to the fundamental work of measuring the cosmic distance ladder. The spacecraft has become a tool for basic astronomy, for measurements that have nothing to do with Pluto or the Kuiper Belt, for science that emerges from the simple fact of being somewhere far away. This versatility reflects the true nature of exploration. Missions are designed with specific objectives in mind, specific questions they intend to answer, specific measurements they plan to make. But the best missions transcend their original designs. They find uses that no one anticipated. They answer questions that had not yet been asked. They contribute to fields that seemed unrelated to their primary purposes. New Horizons was built to study Pluto and Kuiper Belt objects. It has done both brilliantly. But it has also measured the cosmic background radiation, contributed to stellar parallax catalogues, characterized the interplanetary dust environment, mapped the solar wind at unprecedented distances, and demonstrated that small, focused missions can achieve results that rival those of far more expensive programs. The spacecraft continues outward. Each day carries it roughly 1 million miles farther from the Sun, 1 million miles deeper into the cold darkness that fills the outer solar system. Each week adds another 10 million miles to its journey. Each year takes it another astronomical unit from home, another step along a path that will eventually lead beyond the Sun's influence entirely. The plutonium continues decaying, losing roughly 4 watts of power annually, marking time in the currency of nuclear physics rather than human calendars. The instruments continue measuring what they can, recording what they find, storing data against the days when transmission opportunities arise, and those precious measurements can begin their journey back to Earth. The team continues watching, continues planning, continues hoping for one more discovery before the end. They have learned to work within constraints that would have seemed crippling during the primary mission. They have learned to extract maximum value from minimum resources. They have learned that exploration does not end when the original objectives are achieved, that there is always more to discover for those with the patience and creativity to keep looking. The spacecraft that succeeded too well continues finding things nobody planned for, continues returning data from regions no one has ever mapped, continues demonstrating that the outer solar system holds secrets worth pursuing, and still it travels outward, a small machine carrying human curiosity into regions where no human artifact has ever been, where the sun is just a bright star and the familiar landmarks of the inner solar system have shrunk to invisibility. It carries with it not just instruments and recordings and a few ceremonial mementos, but something less tangible and more important: the accumulated effort of thousands of people who spent decades bringing it to life, guiding it across billions of miles, coaxing every possible observation from its aging systems. That effort continues for as long as the spacecraft can respond, for as long as the plutonium can generate enough power to keep the electronics warm and the transmitter active and the cameras functional. The end will come gradually, then suddenly. This is the nature of exponential decay, of systems operating at the margins of their capabilities, of machines that have been pushed far beyond their intended lifespans. For years, the mission team has watched the power levels decline along their inexorable curve, tracking the loss of 4 watts annually, planning each observation campaign around the shrinking energy budget. They have already made painful choices, turning off instruments that once provided valuable data, reducing heating to systems that now operate at temperatures their designers never anticipated. More choices lie ahead. The radioisotope thermoelectric generator that has powered New Horizons since launch contained approximately 11 kilograms of plutonium-238 when it left Earth. That plutonium has been steadily transmuting into uranium-234, releasing alpha particles and generating heat that the thermoelectric couples convert into electricity. At launch, the generator produced roughly 245 watts. By the time of the Pluto encounter, that output had declined to approximately 202 watts. By Arakoth, roughly 190 watts remained. Today, the generator produces somewhere around 170 watts, perhaps slightly less. The spacecraft requires approximately 150 watts to maintain basic operations. This includes keeping the essential electronics warm enough to function, running the onboard computers, and powering the transmitter during communication sessions. The margin between what the generator produces and what the spacecraft needs has been shrinking for years. Each passing month narrows the gap further. Each observation campaign must be balanced against the power required to execute it. The mathematics are unforgiving. At current decay rates, the generator will drop below the minimum threshold for basic operations sometime in the early to mid-2030s. The exact date depends on factors that cannot be precisely predicted. How cold the spacecraft becomes as power declines, how much energy the heaters require to prevent critical components from failing, how efficiently the aging electronics continue to function. But the general trajectory is clear. Within roughly a decade, New Horizons will fall silent. Before that final silence comes a gradual diminishment. The mission team has already begun planning for the cascade of system shutdowns that will precede the end. Some instruments will be powered off permanently to extend the life of others. Some heating circuits will be abandoned, allowing components to cool to temperatures where they can no longer function. Each decision will represent a triage, a choice about which measurements matter most in the time that remains. The Alice ultraviolet spectrometer may be among the first to go. Ultraviolet observations require precise pointing, and as power becomes scarce, the fuel needed for attitude adjustments becomes correspondingly precious. The cosmic optical background measurements that Laurie has been conducting might continue longer, requiring only periodic imaging sessions rather than continuous operation. The dust counter, with its minimal power requirements, could potentially operate until nearly the end. The final observations will likely be simple ones: star fields captured by a failing camera, plasma measurements from sensors operating at the edge of their thermal tolerances, perhaps a last image of the sun, now so distant that it would appear as merely another star among the thousands visible in the field of view. These final data points will be transmitted back to Earth across a gulf so vast that the radio signals will require nearly 5 hours to make the journey, travelling at the speed of light across distances that no human has ever personally experienced. And then, at some point that no one will be able to predict with certainty, the power will drop below the critical threshold. The computers will shut down, the transmitter will fall silent, the last heating elements will lose their battle against the cosmic cold. The temperature inside the spacecraft will begin dropping toward the ambient temperature of deep space, toward the 3 degrees above absolute zero that characterizes the cosmic microwave background radiation, New Horizons will not die so much as gradually freeze into permanent stillness. The plutonium will continue decaying for centuries, but without functioning thermoelectric couples to convert that decay into useful electricity, the spacecraft will become a tomb of frozen electronics. The cameras will point forever at whatever patch of sky they faced when the attitude control system lost power. The antenna will aim at wherever Earth happened to be during the last communication session, though the planet will have moved far from that position within hours of the spacecraft's final transmission. The silence will be absolute. For the first time in decades, the Deep Space Network antennas that have tracked New Horizons will turn to other targets. The mission operations team will disband, their work finally complete. The data archives will be preserved, but no new entries will be added. The story of New Horizons as an active mission will end, but the spacecraft itself will continue travelling outward. Ballistic trajectories do not require power. Newton's first law ensures that an object in motion remains in motion unless acted upon by an external force, and in the vast emptiness of the outer solar system, external forces are few. The Sun's gravity will continue slowing New Horizons' outward progress, but the spacecraft has already achieved escape velocity. It will never fall back. It will never return. The trajectory has been calculated with extraordinary precision. New Horizons will continue moving generally in the direction of the constellation Sagittarius, roughly toward the centre of the Milky Way, though it will never come remotely close to that distant galactic core. In approximately 20,000 years, assuming no gravitational perturbations from objects yet undiscovered, the spacecraft will pass through the inner boundary of the Oort cloud, that vast spherical shell of icy bodies that surrounds the solar system at distances of 2,000 to 200,000 astronomical units from the Sun. The Oort cloud is the ultimate reservoir of cometary material, the source of the long-period comets that occasionally fall inward toward the Sun on journeys lasting millions of years. No spacecraft has ever reached it. No spacecraft currently in flight will reach it within any human lifetime. New Horizons will be among the first human artifacts to enter this uncharted territory, though by then it will have been silent for millennia. In approximately 40,000 years, New Horizons will approach its first star. The trajectory carries it roughly in the direction of a small red dwarf catalogued as AC +79 through 88, currently located in the constellation Camelopardalis. At closest approach, the spacecraft will pass within roughly 0.67 light-years of this unremarkable star, close by interstellar standards, but still vastly farther than the distances that separate planets within solar systems. The star will not capture the spacecraft. New Horizons will pass through its general vicinity and continue onward into the galaxy. The spacecraft that revolutionized our understanding of Pluto, that rewrote textbooks about Kuiper Belt objects, that demonstrated new paradigms for interplanetary exploration, will become an interstellar wanderer. It will drift through the Milky Way for billions of years, outlasting the Sun itself, long after our star has exhausted its hydrogen fuel, expanded into a red giant, shed its outer layers into a planetary nebula, and collapsed into a white dwarf. New Horizons will still be travelling through the galaxy, a small frozen artifact carrying the record of human curiosity into an unimaginably distant future. This trajectory is not unique to New Horizons. Pioneer 10 and Pioneer 11, the Voyager spacecraft and eventually other missions, will follow similar paths into interstellar space. But New Horizons carries something the others do not, a piece of Pluto. Among the ceremonial items aboard the spacecraft are several objects that connect the mission to its scientific and human context. There is an American flag, a tribute to the country that funded and launched the mission. There are 2 state quarters, representing Florida and Maryland, the states where the spacecraft was launched and built respectively. There is a small piece of Spaceship One, the first private spacecraft to reach space, connecting New Horizons to the broader human aspiration to explore beyond Earth. There is a CD-ROM containing 434 awardees and 738 names of people who signed up to have their names sent to Pluto, ordinary individuals who contributed nothing to the mission's funding or execution, but who wanted to participate in some small way in the exploration of the outer solar system. Their names will travel with the spacecraft forever, a modest monument to the public engagement that sustained the mission through its long development and longer cruise, and there are, reportedly, some of the ashes of Clyde Tombaugh, the American astronomer who discovered Pluto in 1930. Tombaugh died in 1997, 9 years before New Horizons launched, but his family arranged for a small container of his cremated remains to be included among the spacecraft's cargo. The man who first detected the pale point of light that would eventually be named Pluto became, in death, the first human to have any part of himself sent beyond the orbit of Neptune. Tombaugh spent 9 months blinking photographic plates at Lowell Observatory in Flagstaff, Arizona, before he found the object that would define his career. He was 24 years old, a farm boy from Kansas, who had built his own telescopes and submitted his observations to the observatory in hopes of securing a position. The discovery made him famous. He spent the rest of his life studying the planets and searching, unsuccessfully, for additional trans-Neptunian objects. He knew that Pluto was a small world, smaller than many moons. He advocated throughout his life for missions to explore it. He never lived to see the spacecraft that would fulfill his vision launch from Cape Canaveral. He never saw the detailed images that would reveal the heart-shaped basin, the nitrogen glaciers, the complex geology of a world he'd known only as a point of light on a photographic plate. But a small portion of his mortal remains completed the journey he could not make, reaching Pluto 85 years after he first detected it from a hilltop in Arizona. The container holding Tombaugh's ashes will travel with New Horizons until the end of the physical universe. It will outlast every person who knew him, every institution that honoured him, every record of his discovery. It will drift through the galaxy while civilizations rise and fall on whatever planets might harbour them. It represents a kind of immortality that no pharaoh's tomb or emperor's monument could ever achieve. Not a static memorial anchored to one world, but a perpetual journey through the cosmos itself. This is perhaps the most appropriate fate for a spacecraft built to explore the unknown. New Horizons was never meant to be a monument. It was meant to be a tool, a scientific instrument designed to answer specific questions about specific objects. It has answered those questions brilliantly. The data it returned has transformed our understanding of the outer solar system, revealing complexity and activity where scientists expected simple, frozen wastelands. But beyond its scientific achievements, New Horizons represents something about the human relationship with the unknown. The spacecraft was conceived during a time when Pluto's status as a planet was being questioned, when some argued that such a small, distant object did not warrant the expense and effort of a dedicated mission. The team that built it faced repeated cancellations, funding crises, and technical challenges that would have defeated less determined advocates. They persisted because they believed that Pluto mattered, that the outer solar system deserved exploration, that the unknown regions beyond Neptune held secrets worth pursuing. They were right. The discoveries at Pluto and Arakoth have vindicated every struggle, every late night, every bureaucratic battle that the mission team fought during the decades of development. The spacecraft that critics called unnecessary has returned data that will shape planetary science for generations. The flyby that skeptics said would reveal only a boring ice ball has shown us one of the most geologically complex and visually stunning worlds in the solar system. And the mission continues. Even now, as the plutonium decays and the power levels decline, New Horizons is making observations that no other instrument can make. The spacecraft's location, 15 billion miles from the Sun and climbing, provides a unique vantage point for studying the interplanetary medium, the cosmic background, and the distribution of dust and plasma in regions that have never been directly sampled. The search for the next flyby target goes on, though the odds grow longer with each passing year. The mission team has not given up hope of finding another Kuiper Belt object within reach before the power runs out. Such a discovery would represent a triumph of determination over probability, a fitting conclusion to a mission that has repeatedly exceeded expectations. But even if no target is found, even if New Horizons never again flies past a world, the spacecraft will continue contributing to science until its final transmission. The legacy extends beyond the data. New Horizons demonstrated that small, focused missions could accomplish what only large, expensive programs had achieved before. It proved that you did not need a Voyager-class budget to explore the outer solar system. It showed that a dedicated team with a clear vision could overcome funding constraints, political obstacles, and technical challenges that would have stopped less committed programs. Future missions to the outer solar system will build on this legacy, inheriting not just the scientific knowledge that New Horizons gathered, but the institutional knowledge of how to build spacecraft that can survive billion-mile journeys on limited budgets. The spacecraft also changed how the public thinks about Pluto. Before New Horizons, Pluto was an abstraction, a dot in photographs, a name that schoolchildren memorized as the 9th planet before it was demoted to dwarf planet status. After New Horizons, Pluto is a place. It has mountains and glaciers and a blue sky. It has weather and geology and a heart. The images that Laurie and Ralph returned in July 2015 transformed Pluto from a concept into a destination, from a data point into a world. Children who were not yet born when New Horizons launched now study those images in school. They see the nitrogen ice of Sputnik Planitia flowing like slow glaciers. They trace the dark equatorial band called Cthulhu Macula. They point to Tombor Regio and ask about the astronomer whose name adorns Pluto's heart. For them, Pluto has always been a world of mountains and glaciers and complex terrain. They do not remember the time when the best images showed only a fuzzy blob. They inherit a solar system that is richer and more detailed than the one their parents knew, and New Horizons made that inheritance possible. The same is true for Arakoth. The contact binary that tumbles through the ancient Kuiper Belt was completely unknown before 2014. No one had ever seen it. No one knew it existed. Its discovery was necessary before New Horizons could even attempt a flyby. And yet today, we have images detailed enough to show individual boulders on its surface. We understand its formation history in ways that seemed impossible before the encounter. We can speak with confidence about processes that occurred 4.6 billion years ago, in the earliest moments of solar system formation, because a spacecraft flew past a tiny rock 30 miles wide at the edge of known space. This is what exploration does. It converts the unknown into the known. It transforms questions into answers. It replaces imagination with observation. The outer solar system that existed before New Horizons was largely a realm of speculation, of theoretical models, of educated guesses based on limited data. The outer solar system that exists after New Horizons is a realm of measured temperatures, catalogued compositions, mapped terrains, and characterized environments. The spacecraft that succeeded too well is now approaching its final chapter. The plutonium that has powered it since launch continues its slow transformation into uranium. The electronics that have operated far beyond their design lifetimes continue functioning through some combination of robust engineering and simple luck. The team that has guided the spacecraft across 4 billion miles continues planning observations, writing proposals, extracting every possible measurement from their aging but still capable explorer. When the end comes, it will come quietly. There will be no dramatic explosion, no final crash, no spectacular conclusion. The spacecraft will simply stop responding. The last transmission will be recorded, analysed, archived. The Deep Space Network will try to re-establish contact, following protocols designed for exactly this contingency. They will send commands, listen for responses, wait with diminishing hope as hours turn into days. Eventually someone will make the official determination that the mission has ended. There will be press releases and commemorative statements. The mission team will gather, perhaps for the last time, to mark the end of an endeavour that has occupied decades of their lives. Scientists who began as graduate students will have reached retirement. Engineers who designed systems for launch will have seen those systems outlive their most optimistic projections. Program managers who fought for funding will have won battles that seemed hopeless at the time. And somewhere in the outer solar system, beyond the orbit of Pluto, beyond Arakoth, beyond any object that humans have ever studied up close, a small spacecraft will continue its journey. It will carry its frozen instruments, its ceremonial cargo, its accumulated data and memories into the interstellar void. It will become a permanent part of the galaxy, a human artifact drifting through stellar neighbourhoods that we cannot yet name. The sun will continue shrinking in New Horizons' rearview mirror if the spacecraft could still look back. It is already just a bright star from the spacecraft's perspective, not the overwhelming presence it seems from Earth. Eventually it will fade into the background, indistinguishable from millions of other stars. The spacecraft will have truly left home, but it will not be alone. Voyager 1 and Voyager 2 are already there, crossing the heliopause into interstellar space. Pioneer 10 and Pioneer 11 preceded them. New Horizons will eventually join this small fleet of human emissaries, artifacts that represent the furthest physical reach of human civilization. They carry different instruments, different missions, different cargoes. but they share a common purpose: to go where nothing from Earth has ever been, to measure what has never been measured, to explore what has never been explored. New Horizons succeeded beyond anyone's expectations. It launched when many thought it would never fly. It reached Pluto when skeptics doubted the value of the journey. It found Arakoth when the odds of locating a suitable target seemed impossibly long. It continues operating when its power budget should have forced shutdown years ago. The spacecraft is a testament to human persistence, to the stubborn refusal to accept limitations as permanent. It demonstrates that the outer solar system is not too distant, not too dark, not too cold for exploration. It proves that small teams with big dreams can achieve what once seemed impossible. The next spacecraft to visit the outer solar system, whenever it launches, will build on everything New Horizons learned. It will benefit from the detailed maps, the composition measurements, the atmospheric data that New Horizons gathered. It will approach the Kuiper Belt with knowledge that did not exist before 2015, understanding that emerged from the successful encounter with Pluto and Arakoth. And somewhere in the dark, travelling ever outward, New Horizons will continue its journey. The spacecraft that was built for one flyby, that succeeded too well, that keeps finding things nobody planned for, will become a permanent ambassador to the cosmos. It will carry the record of human curiosity into the galaxy, a small machine bearing witness to what we chose to do when we reached for the farthest horizons we could imagine. The outer solar system is no longer unknown. New Horizons saw to that. The darkness beyond Neptune now has texture, has detail, has secrets revealed, and mysteries remaining. The spacecraft proved that even the most distant shores can be reached by those with patience, determination, and the audacity to try. The journey continues, the power fades, the distance grows, but the data remain, the discoveries endure, and the legacy persists. A small spacecraft, travelling 1,000,000 miles each day towards stars it will never reach in any human lifetime, demonstrates a truth that transcends the particulars of any single mission. The universe rewards those who seek to understand it. The unknown reveals itself to those who make the effort to look. New Horizons looked, and Pluto gazed back with a heart of nitrogen ice. The spacecraft succeeded too well, and the outer solar system will never be the same.